Warning: empty page. Fundamentals of Digital Logic with Verilog Design 3rd edition, Stephen Brown and Zvonko Vranesic, Department of Electrical and Computer Engineering, University of Toronto. Fundamentals of Digital Logic with Verilog Design 3rd edition. Published by McGraw-Hill, a business unit of the McGraw-Hill Companies Incorporated, 1221 Avenue of the Americas, New York, New York, 10020. Copyright 2014 by the McGraw-Hill Companies Incorporated. All rights reserved. No part of this publication may be reproduced or distributed in any form or by any means, or stored in a database or retrieval system, without the prior written consent of the McGraw-Hill Companies, Inc., including but not limited to, in any network or other electronic storage or transmission, or broadcast for distance learning. Some ancillaries, including electronic and print components, may not be available to customers outside the United States. This book is printed on acid-free paper. 12345678890 doc/doc1098765543 ISBN 978-0-07-338054-4 MHID 0-07-338054-7. Managing Director, Thomas Tim. Director, Michael Lang. Global Publisher, Raghuthaman Srinivasan. Developmental Editor, Vincent Bradshaw. Marketing Manager, Kurt Reynolds. Director, Content Production, Terry Sheasel. Senior Project Manager, Melissa M. Leek-Buyer, Susan K. Culbertson. Media Project Manager, Prashanthi Nadapalli. Cover Design, Studio Montage, St. Louis, Missouri. Use Cover Image, Stephen Brown and Zvonko Vranesic. Compositor, TextEditors Incorporated. Typeface, 10/12 times Roman Printer, R. Donley, Crawfordsville, Indiana. Library of Congress. Cataloging and Publication Data. Brown, Stephen. Fundamentals of Digital Logic with Verilog Design / Stephen Brown and Zvonko Vranesic. 3rd edition.
Pakiscm ISTN 97880733804 alkaen.
Paper 1. Logic Circuits Design and Construction Data Processing. 2. Verilog Computer Hardware Description Language. 3. Computer-Aided Design.
Vranesic, Zvonko G. Drugi.
Title: TK7868, L6B76 2014 621.392, DC 23201, 204, 2163 www. MHHE.com. To Susan and Anne. This page intentionally left blank. About the authors. Stephen Brown received his Bachelor's of Science degree in Electrical Engineering from the University of New Brunswick, Canada, and the MESc and PhD degrees in Electrical Engineering from the University of Toronto. He joined the University of Toronto faculty in 1992, where he is now a professor in the Department of Electrical and Computer Engineering. He is also the director of the Worldwide University Program at Altera Corporation. His research interests include field programmable VLSI technology and computer architecture. He won the Canadian Natural Sciences and Engineering Research Council's 1992 Doctoral Prize for the Best PhD thesis in Canada and has published more than 100 scientific research papers. He has won 5 awards for excellence in teaching electrical engineering, computer engineering, and computer science courses. He is a co-author of 2 other books, Fundamental Soft Digital Logic with VHDL Design, 3rd edition, and Field Programmable Gate Arrays. Zvonko Vranesic received his Bachelor's of Science, MASc, and PhD degrees, all in electrical engineering, from the University of Toronto. From 1963 to 1965, he worked as a design engineer with the Northern Electric Company, Limited in Bramalea, Ontario. In 1968, he joined the University of Toronto, where he is now a professor emeritus in the departments of Electrical and Computer Engineering and Computer Science. During the 1978 to 1979 academic year, he was a senior visitor at the University of Cambridge, England, and during 1984 to 1985, he was at the University of Paris, 6. From 1995 to 2000, he served as chair of the Division of Engineering Science at the University of Toronto. He is also involved in research and development at the Altera Toronto Technology Centre. His current research interests include computer architecture and field programmable VLSI technology. He is a co-author of 4 other books: Computer Organization and Embedded Systems, 6th edition, Fundamentals of Digital Logic with VHDL Design, 3rd edition, Microcomputer Structures, and Field Programmable Gate Arrays. In 1990, he received the Whiten Fellowship for innovative and distinctive contributions to undergraduate laboratory instruction. In 2004, he received the Faculty Teaching Award from the Faculty of Applied Science and Engineering at the University of Toronto. He has represented Canada in numerous chess competitions. He holds the title of International Master.
V.
Preface. This book is intended for an introductory course in digital logic design, which is a basic course in most electrical and computer engineering programs. A successful designer of digital logic circuits needs a good understanding of basic concepts and a firm grasp of the modern design approach that relies on computer-aided design, CAD, tools. The main goals of the book are 1. To teach students the fundamental concepts in classical manual digital design, and 2. Illustrate clearly the way in which digital circuits are designed today, using CAD tools. Even though modern designers no longer use manual techniques, except in rare circumstances, our motivation for teaching such techniques is to give students an intuitive feeling for how digital circuits operate. Also, the manual techniques provide an illustration of the types of manipulations performed by CAD tools, giving students an appreciation of the benefits provided by design automation. Throughout the book, basic concepts are introduced by way of examples that involve simple circuit designs, which we perform using both manual techniques and modern CAD tool-based methods. Having established the basic concepts, more complex examples are then provided, using the CAD tools. Thus, our emphasis is on modern design methodology to illustrate how digital design is carried out in practice today.
Technology.
The book discusses modern digital circuit implementation technologies. The emphasis is on programmable logic devices, PLDs, which is the most appropriate technology for use in a textbook for 2 reasons. First, PLDs are widely used in practice and are suitable for almost all types of digital circuit designs. In fact, students are more likely to be involved in PL-based designs at some point in their careers than in any other technology. Second, circuits are implemented in PLDs by end-user programming. Therefore, students can be provided with an opportunity, in a laboratory setting, to implement the book's design examples in actual chips. Students can also simulate the behavior of their design circuits on their own computers. We use the 2 most popular types of PLDs for targeting of designs: complex programmable logic devices, CPLDs, and field programmable gate arrays, FPGAs. We emphasize the use of a hardware description language in specifying the logic circuits because the HDL-based approach is the most efficient design method to use in practice. We describe in detail the IEEE standard Verilog HDL language and use it extensively in examples. 6. Preface. 7. Scope of the book. This edition of the book has been extensively restructured. All of the material that should be covered in a 1-semester course is now included in chapters 1 to 6. More advanced material is presented in chapters 7 to 11. Chapter 1 provides a general introduction to the process of designing digital systems. It discusses the key steps in the design process and explains how CAD tools can be used to automate many of the required tasks. It also introduces the representation of digital information. Chapter 2 introduces the logic circuits. It shows how Boolean algebra is used to represent such circuits. It introduces the concepts of logic circuit synthesis and optimization and shows how logic gates are used to implement simple circuits. It also gives the reader a first glimpse at Verilog as an example of a hardware description language that may be used to specify the logic circuits. Chapter 3 concentrates on circuits that perform arithmetic operations. It discusses number sand shows how they can be manipulated using logic circuits. This chapter illustrates how Verilog can be used to specify the desired functionality and how CAD tools provide a mechanism for developing the required circuits. Chapter 4 presents combinational circuits that are used as building blocks. It includes the encoder, decoder, and multiplexer circuits. These circuits are very convenient for illustrating the application of many Verilog constructs, giving the reader an opportunity to discover more advanced features of Verilog. Storage elements are introduced in Chapter 5. The use of flip-flops to realize regular structures, such as shift registers and counters, is discussed. Verilog-specified designs of these structures are included. Chapter 6 gives a detailed presentation of synchronous sequential circuits, finite state machines. It explains the behavior of these circuits and develops practical design techniques for both manual and automated design. Chapter 7 is a discussion of a number of practical issues that arise in the design of real systems. It highlights problems often encountered in practice and indicates how they can be overcome. Examples of larger circuits illustrate a hierarchical approach in designing digital systems. Complete Verilog code for these circuits is presented. Chapter 8 deals with more advanced techniques for optimized implementation of logic functions. It presents algorithmic techniques for optimization. It also explains how logic functions can be specified using a cubical representation, as well as using binary decision diagrams. Asynchronous sequential circuits are discussed in Chapter 9. While this treatment is not exhaustive, it provides a good indication of the main characteristics of such circuits. Even though the asynchronous circuits are not used extensively in practice, they provide an excellent vehicle for gaining a deeper understanding of the operation of digital circuits in general. They illustrate the consequences of propagation delays and race conditions that may be inherent in the structure of a circuit. Chapter 10 presents a complete CAD flow that the designer experiences when designing, implementing, and testing a digital circuit. 8. Preface. Chapter 11 introduces the topic of testing. A designer of logic circuits has to be aware of the need to test circuits and should be conversant with at least the most basic aspects of testing. Appendix A provides a complete summary of Verilog features. Although use of Verilog is integrated throughout the book, this appendix provides a convenient reference that the reader can consult from time to time when writing Verilog code. The electronic aspects of digital circuits are presented in Appendix B. This appendix shows how the basic gates are built using transistors and presents various factors that affect circuit performance. The emphasis is on the latest technologies, with particular focus on CMOS technology and programmable logic devices. What can be covered in a course? Much of the material in the book can be covered in 2 one-quarter courses. A good coverage of the most important material can be achieved in a single one-semester or even a quarter course. This is possible only if the instructor does not spend too much time teaching the intricacies of Verilog and CAD tools. To make this approach possible, we organize the Verilog material in a modular style that is conducive to self-study. Our experience in teaching different classes of students at the University of Toronto shows that the instructor may spend only 3 to 4 lecture hours on Verilog, describing how the code should be structured, including the use of design hierarchy, using scalar and vector variables, and on the style of code needed to specify sequential circuits. The Verilog examples given in the book are largely self-explanatory and students can understand them easily. The book is also suitable for a course in logic design that does not include exposure to Verilog. However, some knowledge of Verilog, even at a rudimentary level, is beneficial to the students, and it is a great preparation for a job as a design engineer. One-semester course. The following material should be covered in lectures. Chapter 1 All sections. Chapter 2 All sections. Chapter 3 Sections 3.1 to 3.5. Chapter 4 All sections. Chapter 5 All sections. Chapter 6 All sections. One-quarter course. In a one-quarter course, the following material can be covered. Chapter 1 All sections. A Chapter 2 All sections. Preface. Chapter 3 Sections 3.1 to 3.3 and Section 3.5. A Chapter 4 All sections. A Chapter 5 All sections. A Chapter 6 Sections 6.1 to 6.4. Verilog. Verilog is a complex language which some instructors feel is too hard for beginning students to grasp. We fully appreciate this issue and have attempted to solve it. It is not necessary to introduce the entire Verilog language. In the book, we present the important Verilog constructs that are useful for the design and synthesis of logic circuits. Many other language constructs, such as those that have meaning only when using the language for simulation purposes, are omitted. The Verilog material is introduced gradually, with more advanced features being presented only at points where their use can be demonstrated in the design of relevant circuits. The book includes more than 120 examples of Verilog code. These examples illustrate how Verilog is used to describe a wide range of logic circuits, from those that contain only a few gates to those that represent digital systems, such as a simple processor. All of the examples of Verilog code presented in the book are provided on the author's website at www.toronto.edu/tilde_Brown/Verilog_3 solved problems. The chapters include examples of solved problems. They show how typical homework problems may be solved. Homework problems. More than 400 homework problems are provided in the book. Answers to selected problems are given at the back of the book. Solutions to all problems are available to instructors in the solutions manual that accompanies the book. PowerPoint slides and solutions manual. PowerPoint slides that contain all of the figures in the book are available on the author's website. Instructors can request access to these slides, as well as access to the solutions manual for the book, at www.mhhe.com/brownvranesic. Preface. CAD tools. Modern digital systems are quite large. They contain complex logic circuits that would be difficult to design without using good CAD tools. Our treatment of Verilog should enable the reader to develop Verilog code that specifies logic circuits of varying degrees of complexity. To gain proper appreciation of the design process, it is highly beneficial to implement the designs using commercially available CAD tools. Some excellent CAD tools are available free of charge. For example, the Altera Corporation has its Quartus 2 CAD software, which is widely used for implementing designs in programmable logic devices such as FPGAs. The web edition of the Quartus 2 software can be downloaded from Altera's website and used free of charge, without the need to obtain a license. In previous editions of this book, a set of tutorials for using the Quartus 2 software was provided in the appendices. Those tutorials can now be found on the author's website. Another set of useful tutorials about Quartus 2 can be found on Altera's University Program website, which is located at www.altera.com/education/university. Acknowledgements. We wish to express our thanks to the people who have helped during the preparation of the book. Dan Vranesic produced a substantial amount of artwork. He and D. Shannon Singh also helped with the preparation of the solutions manual. Tom Chakowski helped in checking the answers to some problems. The reviewers: William Barnes, New Jersey Institute of Technology; Thomas Bradikich, North Carolina State University; James Clark, McGill University; Stephen DeWorth, Georgia Institute of Technology; Sander Eller, Cal Poly Pomona; Clay Gloucester, Jr., North Carolina State University, Raleigh; Carl Hamaker, Queen's University; Vincent Herring, University of Colorado; Yuhen Hu, University of Wisconsin; Wei-Ming Lin, University of Texas, San Antonio; Wayne Laux, University of Waterloo; Kartik Mohan Ram, Rice University; Jane Moorhead, Mississippi State University; Chris Myers, University of Utah; Vajan Oklabzija, University of California, Davis; James Palmer, Rochester Institute of Technology; Gandhi Pavada, University of Southern California; Teodoro Robles, Milwaukee School of Engineering; Tatiana Rosener, Boston University; Rob Rittenbar, Carnegie Mellon University; Eric Schwartz, University of Florida; Wonsong Shiu, Oregon State University. Peter Simcoe, Miami University. Scott Smith, University of Missouri, Rolla. Arun Samani, Iowa State University. Bernard Svile, University of Texas, Arlington. And Željko Zilic, McGill University, provided constructive criticism and made numerous suggestions for improvements. The support of McGraw-Hill people has been exemplary. We truly appreciate the help of Raghu Srinivasan, Vincent Bradshaw, Darlene Schuler, Kurt Reynolds, and Michael Lang. We are also grateful for the excellent support in the typesetting of the book that has been provided by TextEditors Incorporated Stephen Brown and Zvonko Vranesic. Contents CHAPTER 1 Introduction 1.1 Digital Hardware 2 1.1.1 Standard Chips 4 1.1.2 Programmable Logic Devices 5 1.1.3 Custom Design Chips 5 1.2 The Design Process 6 1.3 Structure of a Computer 8 1.4 Logic Circuit Design. In this book, 8 1.5 Digital Representation of Information 11 1.5.1 Binary Numbers 12 1.5.2 Conversion between Decimal and Binary Systems 13 1.5.3 SCI Character Code 14 1.5.4 Digital and Analog Information 16 1.6 Theory and Practice 16 Problems 18 References 19 CHAPTER 2 Introduction to Logic Circuits 21 2.1 Variables and Functions 22 2.2 Inversion 25 2.3 Truth Tables 26 2.4 Logic Gates and Networks 27 2.4.1 Analysis of a Logic Network 29 2.5 Boolean Algebra 33 2.5.1 The Venn Diagram 37 2.5.2 Notation and Terminology 422.5.3 Precedence of Operations 43 2.6 Synthesis using or, and not gates 43 2.6.1 Sum of products and product of sums forms 48 2.7 NAND and NOR logic networks 54 2.8 Design examples 59 2.8.1 Three-way light control 59 2.8.2 Multiplexer circuit 62.8.3 Number display 63 2.9 Introduction to CAD tools 64 2.9.1 Design entry 64 2.9.2 Logic synthesis 66 2.9.3 Functional Simulation 67 2.9.4 Physical Design 67 2.9.5 Timing Simulation 67 2.9.6 Circuit Implementation 68 2.9.7 Complete Design Flow 68 2.10 Introduction to Verilog 68 2.10.1 Structural Specification of Logic Circuits 72.10.2 Behavioral Specification of Logic Circuits 72 2.10.3 Hierarchical Verilog Code 76 2.10.4 How Not to Write Verilog Code 78 2.11 Minimization and Karnaugh Map 78 2.12 Strategy for Minimization 87 2.12.1 Terminology 87 2.12.2 Minimization Procedure 89 2.13 Minimization of Product of Sums Forms 91 2.14 Incompletely Specified Functions 94 2.15 Multiple Output Circuits 96 2.16 Concluding Remarks 101 2.17 Examples of Solved Problems 101 Problems 111 References 120 CHAPTER 3 Number Representation and Arithmetic Circuits 121 3.1 Positional Number Representation 122 3.1.1 and Signed Integers 122 3.1.2 Octal and Hexadecimal Representations 123 3.2 Addition of unsigned numbers 125 3.2.1 Decomposed full adder 129 3.2.2 Ripple carry adder 129 3.2.3 Design example 13011 12 Contents 3.3 Sign numbers 132 3.3.1 Negative numbers 133 3.3.2 Addition and subtraction 135 3.3.3 Adder and subtractor unit 138 3.3 3.4 radix complement schemes asterisk operator 139. 3.3.5 arithmetic overflow 143, 3.3.6 performance issues 145, 3.4 fast adders 145, 3.4.1 carry look ahead adder 146, 3.5 design of arithmetic circuits using CAD tools 151. 3.5.1 design of arithmetic circuits using schematic capture 151, 3.5.2 design of arithmetic circuits using Verilog 152, 3.5.3 using vectored signals 155, 3.5.4 using a generic specification 156. 3.5.5 nets and variables in Verilog 158, 3.5.6 arithmetic assignment statements 159, 3.5.7 module hierarchy in Verilog code 163. 3.5.8 representation of numbers in Verilog code 166, 3.6 multiplication 167, 3.6.1 array multiplier for unsigned numbers 167, 3.6.2 multiplication of signed numbers 169. 3.7 Other number representations 170, 3.7.1 Fixed point numbers 170, 3.7.2 Floating point numbers 172, 3.7.3 Binary coded decimal representation 174. 3.8 Examples of solved problems 178 problems 184 References 188 CHAPTE R4 Combinational circuit building blocks 189 4.1 Multiplexers 190 4.1.1 Synthesis of logic functions using multiplexers 193 4.1.2 Multiplexer synthesis using Shannon's expansion 196 4.2 Decoders 201 4.2.1 Demultiplexers 203 4.3 Encoders 205 4.3.1 Binary encoders 205 4.3.2 Priority encoders 205 4.4 Code converters 208 4.5 Arithmetic comparison circuits 208 4.6 Verilog for combinational circuits 210 4.6.1 The conditional operator 210 4.6.2 The if-else statement 212 4.6.3 The case statement 215 4.6.4 The for loop 221 4.6.5 Verilog operators 223 4.6.6 The generate construct 228 4.6.7 Tasks and functions 229 4.7 Concluding remarks 232 4.8 Examples of solved problems 233 problems 243 References 246 CHAPTE R5 Flip-flops, registers, and counters 247 5.1 Basic latch 249 5.2 Gated SR latch 251 5.2.1 Gated SR latch with NAND gates, 253 5.3 Gated D latch, 253 5.3.1 Effects of propagation delays, 255 5.4 Edge triggered D flip-flops, 256 5.4.1 Master slave D flip-flop 256 5.4.2 Other types of edge-triggered D flip-flops, 258 5.4.3 D flip-flops with clear and preset, 265.4.4 flip-flop timing parameters, 2635.5 T flip-flop 263 5.6 JK flip-flop 264 5.7 Summary of terminology 266 5.8 Registers 267 5.8.1 Shift register 267 5.8.2 Parallel access Shift register 267 5.9 Counters 269 5.9.1 Asynchronous counters 269 5.9.2 Synchronous counters 272 5.9.3 Counters with parallel load 276 5.10 Reset synchronization 278 5.11 Other types of counters 285.11.1 BCD counter 285.11.2 Ring counter 280 Contents 13.5.11.3 Johnson counter 283.5.11.4 Remarks on counter design 283.5.12 Using storage elements with CAD tools 284.5.12.1 Including storage elements in schematics 284. 5.12.2 Using Verilog constructs for storage elements 285.5.12.3 Blocking and non-blocking assignments 288.5.12.4 Non-blocking assignments for combinational circuits 293. 5.12.5 Flip-flops with clear capability 293.5.13 Using Verilog constructs for registers and counters 295.5.13.1 Flip-flops and registers with enable inputs 300. 5.13.2 Shift registers with enable inputs 3025.14 Design example 3025.14.1 Reaction timer 3025.14.2 Register transfer level RTL code 3095.15 Timing analysis of flip-flop circuits 310. 5.15.1 Timing analysis with clock skew 312.5.16 Concluding remarks 314.5.17 Examples of solved problems 315 Problems 321 References 329 CHAPTE R6 Synchronous sequential circuits 331. 6.1 Basic design steps 333 6.1.1 State diagram 333 6.1.2 State table 335 6.1.3 State assignment 336 6.1.4 Choice of flip-flops and derivation of next state and output expressions 337. 6.1.5 Timing diagram 339 6.1.6 Summary of design steps 340 6.2 State assignment problem 344 6.2.11 Hot encoding 347 6.3 Mealy state model 349. 6.4 Design of finite state machines using CAD tools 354 6.4.1 Verilog code for more type FSMs 355 6.4.2 Synthesis of Verilog code 356 6.4.4 Alternative styles of Verilog code 359. 6.4.5 Summary of design steps when using CAD tools 360 6.4.6 Specifying the state assignment in Verilog code 361 6.4.7 Specification of Mealy FSMs using Verilog 3636.5 Serial adder example 363. 6.5.1 Mealy type FSM for serial adder 364 6.5.2 More type FSM for serial adder 367 6.5.3 Verilog code for the serial adder 376.6 State minimization 372. 6.6.1 Partitioning minimization procedure 374 6.6.2 Incompletely specified FSMs 381 6.7 Design of a counter using the sequential circuit approach 383. 6.7.1 State diagram and state table for a modulo 8 counter 383 6.7.2 State assignment 384 6.7.3 Implementation using D-type flip-flops 385 6.7.4 Implementation using JK-type flip-flops 386. 6.7.5 Example A Different counter 396.8 FSM as an arbiter circuit 393 6.9 Analysis of synchronous sequential circuits 397 6.10 Algorithmic state machine ASM charts 401. 6.11 Formal model for sequential circuits 405 6.12 Concluding remarks 407 6.13 Examples of solved problems 407 Problems 416 References 420 CHAPTE R7 Digital system design 421. 7.1 Bus structure 422 7.1.1 Using tri-state drivers to implement a bus 422 7.1.2 Using multiplexers to implement a bus 424 7.1.3 Verilog code for specification of bus structures 426. 7.2 Simple processor 429 6.4.3 Simulating and testing the circuit 358. 14 Content 7.3a Bit Counting Circuit 441 7.4 Shift and Add Multiplier 446 7.5 Divider 455 7.6 Arithmetic Mean 466 7.7 Sort Operation 477.8 Clock Synchronization and Timing Issues 478 7.8.1 Clock Distribution 478 7.8.2 Flip-flop Timing Parameters 481 7.8.3 Asynchronous Inputs to Flip-flops 482 7.8.4 Switch Debouncing 483 7.9 Concluding Remarks 485 Problems 485 References 489 CHAPTER 8 Optimized Implementation of Logic Functions 491 8.1 Multilevel Synthesis 492 8.1.1 Factoring 493 8.1.2 Functional Decomposition 496 8.1.3 Multilevel NAND and NOR Circuits 502 8.2 Analysis of Multilevel Circuits 504 8.3 Alternative Representations of Logic Functions 510 8.3.1 Cubical Representation 510 8.3.2 Binary Decision Diagrams 514 8.4 Optimization Techniques based on cubical representation 528.4.1 A tabular method for minimization 521 8.4.2 A cubical technique for minimization 529 8.4.3 Practical considerations 536 8.5 Concluding Remarks 537 8.6 Examples of solved problems 537 Problems 546 References 549 9.3 Synthesis of asynchronous circuits 564 9.4 State reduction 577 9.5 State assignment 592 9.5.1 Transition Diagram 595 9.5.2 Exploiting unspecified next state entries 598 9.5.3 State assignment using additional state variables 602 9.5.4 Hot state assignment 607 9.6 Hazard 608 9.6.1 Static hazard 609 9.6.2 Dynamic hazard 613 9.6.3 Significance of hazard 614 9.7 A complete design example 616 9.7.1 The vending machine controller 616 9.8 Concluding remarks 621 9.9 Examples of solved problems 623 Problems 631 References 635 CHAPTER 10 Computer-aided design tools 637 10.1 Synthesis 638 10.1.1 Netlist generation 638 10.1.2 Gate optimization 638 10.1.3 Technology Mapping 640 10.2 Physical Design 644 10.2.1 Placement 646 10.2.2 Routing 647 10.2.3 Static Timing Analysis 648 10.3 Concluding Remarks 650 References 651 CHAPTER 11 Testing of logic circuits 653 11.1 Fault model 654 1.1.1 Stuck at model 654 1.1.2 Single and multiple faults 655 CHAPTER 911.1.3 CMOS circuits 655 11.2 Complexity of a test set 655 Asynchronous sequential circuits 551 11.3 Path sensitizing 657 1.3.1 Detection of a specific fault 659 9.1 Asynchronous behavior 552 11.4 Circuits with tree structure 661 9.2 Analysis of asynchronous circuits 556 11.5 Random tests 662 Contents 15 11.6 Testing of sequential circuits 665 1.6.1 Design for testability 665 11.7 Built-in self-test 669 1.7.1 Built-in logic block observer 673 1.7.2 Signature analysis 675 1.7.3 boundary, scan 676.11.8 printed circuit boards 676.11.8.1 testing of PCBs 678.11.8.2 instrumentation 679.11.9 concluding remarks 680 problems 680 references 683 Number representation and arithmetic circuits 121. CHAPTE are 3 number representation and arithmetic circuits. Chapter objectives. In this chapter you will learn about representation of numbers in computers, circuits used to perform arithmetic operations, performance issues in large circuits, use of Verilog to specify arithmetic circuits. 121. 122 number representation and arithmetic circuits, CHAPTE, R3. In this chapter we will discuss logic circuits that perform arithmetic operations. We will explain how numbers can be added, subtracted, and multiplied. We will also show how to write Verilog code to describe the arithmetic circuits. These circuits provide an excellent platform for illustrating the power and versatility of Verilog in specifying complex logic circuit assemblies. The concepts involved in the design of arithmetic circuits are easily applied to a wide variety of other circuits. Before tackling the design of arithmetic circuits, it is necessary to discuss how numbers are represented in digital systems. In Chapter 1 we introduced binary numbers and showed how they can be expressed using the positional number representation. We also discussed the conversion process between decimal and binary number systems. In Chapter 2 we dealt with logic variables in a general way, using variables to represent either the states of switches or some general conditions. Now we will use the variables to represent numbers. Several variables are needed to specify a number, with each variable corresponding to one digit of a number. 3.1 Positional number representation. When dealing with numbers and arithmetic operations, it is convenient to use standard symbols. Thus, to represent addition, we use the plus symbol, and for subtraction, we use the minus symbol. In Chapter 2, we use the plus symbol mostly to represent the logical or operation. Even though we will now use the same symbols for 2 different purposes, the meaning of each symbol will usually be clear from the context of the discussion. In cases where there may be some ambiguity, the meaning will be stated explicitly. 3.1.1 Unsigned integers. The simplest numbers to consider are the integers. We will begin by considering positive integers and then expand the discussion to include negative integers. Numbers that are positive only are called unsigned, and numbers that can also be negative are called signed. Representation of numbers that include a radix point real numbers is discussed later in the chapter. As explained in section 1.5.1, an n-bit unsigned number b equals bn minus 1 bn minus 2, b1 b0. Represents an integer that has the value 2n minus 1 plus 2n minus 2 plus 21 plus 20 b equals bn minus 1 times bn minus 2 times, plus b1 times b0 times n minus 1 3.1 by 2 I equals times I equals 0. 3.1 Positional number representation. 3.1.2 Octal and hexadecimal representations. The positional number representation can be used for any radix. If the radix is r, then the number k equals kn minus 1 kn minus 2, k1 k0 has the value n minus 1 key v, k equals times I equals 0. Our interest is limited to those radices that are most practical. We will use decimal numbers because they are used by people, and we will use binary numbers because they are used by computers. In addition, two other radices are useful, 8 and 16. Numbers represented with radix 8 are called octal numbers, while radix 16 numbers are called hexadecimal numbers. In octal representation, the digit values range from 0 to 7. In hexadecimal representation, often abbreviated as hex, each digit can have one of 16 values. The first 10 are denoted the same as in the decimal system, namely 0 to 9. Digits that correspond to the decimal values 10, 11, 12, 13, 14, and 15 are denoted by the letters A, B, C, D, E, and F. Table 3.1 gives the first 18 integers in these number systems. In computers, the dominant number system is binary. The reason for using the octal and hexadecimal systems is that they serve as a useful shorthand notation for binary numbers. One octal digit represents 3 bits. Thus, a binary number is converted into an octal number. Table 3.1 numbers in different systems. Decimal binary octal hexadecimal 000000000000001 00 001 01 0102 09010000010 0901001 11 09 1001010 12 0 A 11 0 10 11 13 0 B 12 0 11 0 0 14 0 C 13 0 11 0 115 0 D 14 0 1110 16 0 E 15 01111 17 0 F 16 100 00 20 10 17 100 01 21 11 18 100 10 22 12 124 number representation and arithmetic circuits CHAPTER3. By taking groups of 3 bits, starting from the least significant bit and replacing them with the corresponding octal digit. For example, 10101101 0111 is converted as 1010110111 5327, which means that 10101101 0111 2 equals 5327 8. If the number of bits is not a multiple of 3, then we add zeros to the left of the most significant bit. For example, 10111011 2 equals 273 8 because of the grouping 01011101127 conversion from octal to binary is just as straightforward. Each octal digit is simply replaced by 3 bits that denote the same value. Similarly, a hexadecimal digit represents 4 bits. For example, a 16-bit number is represented by 4 hex digits, as in 10101100100101 2 equals AF 25 16. Using the grouping 10111100100101 AF 25. Zeros are added to the left of the most significant bit if the number of bits is not a multiple of 4. For example, 110110100 2 equals 368 16 because of the grouping 00110110100. 368 conversion from hexadecimal to binary involves straightforward substitution of each hex digit by 4 bits that denote the same value. Binary numbers used in modern computers often have 32 or 64 bits. Written as binary n-tuples, sometimes called bit vectors, such numbers are awkward for people to deal with. It is much simpler to deal with them in the form of 8 or 16-digit hex numbers. Because the arithmetic operations in a digital system usually involve binary numbers, we will focus on circuits that use such numbers. We will sometimes use the hexadecimal representation as a convenient shorthand description. We have introduced the simplest numbers and signed integers. It is necessary to be able to deal with several other types of numbers. We will discuss the representation of signed numbers, fixed point numbers, and floating point numbers later in this chapter. But first we will examine some simple circuits that operate on numbers to give the reader a feeling for digital circuits that perform arithmetic operations and to provide motivation for further discussion. 3.2 Addition of unsigned numbers. 3.2 Addition of unsigned numbers. Binary addition is performed in the same way as decimal addition except that the values of individual digits can be only 0 or 1. In Chapter 2, we already considered the addition of two 1-bit numbers as an example of a simple logic circuit. Now, we will consider this task in the context of general ladder circuits. The 1-bit addition entails 4 possible combinations, as indicated in Figure 3.1a. 2 bits are needed to represent the result of the addition. The rightmost bit is called the sum, S. The leftmost bit, which is produced as a carry-out when both bits being added are equal to 1, is called the carry, C. The addition operation is defined in the form of a truth table in part B of the figure. The sum bit S is the XOR function. The carry C is the AND function of inputs X and Y. A circuit realization of these functions is shown in Figure 3.1c. This circuit, which implements the addition of only 2 bits, is called a half-adder. X0, 0, 1, 1 plus, Y plus 0 plus 1 plus 0 plus 1 CS. 0, 0, 0, 1, 0, 1, 1, 0 sum carry. A. The 4 possible cases carry sum X, Y, CS 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0. B. Truth table XYS, CHA XYSC. C. Circuit. D. Graphical symbol Figure 3.1 half-adder. 126 Number representation and arithmetic circuits CHAPTER3 generated carries 1110. CI plus CI 1x equals x4 x3 x2 x1 x0 0 1 1 1 1 15 10 11 plus y equals y4 y3 y2 y1 y0 0 1 0 1 0 plus 10 10 plus E.
S uguale S4 S3 S2 S1 S0 1 1 0 0 1 25 10. C.
A. An example of addition. B. Bit position. I. Figure 3.2 addition of multi-bit numbers. A more interesting case is when larger numbers that have multiple bits are involved. Then it is still necessary to add each pair of bits, but for each bit position I, the addition operation may include a carry-in from bit position I-1. Figure 3.2 presents an example of the addition operation. The two operands are x equals 0, 1, 1, 1, 1, 2 equals 15, 10, and y equals 0, 1, 0, 1, 0, 2 equals 10, 10. 5 bits are used to represent x and y, making it possible to represent integers in the range from 0 to 31. Hence the sum s equals x plus y equals 25. 10 can also be denoted as a 5-bit integer. Note the labeling of individual bits, such that x equals x4, x3, x2, x1, x0, and y equals y4, y3, y2, y1, y0. The figure shows, in a blue color, the carries generated during the addition process. For example, a carry of 0 is generated when x0 and y0 are added. A carry of 1 is produced when x1 and y1 are added, and so on. In Chapter 2, we designed logic circuits by first specifying their behavior in the form of a truth table. This approach is impractical in designing an adder circuit that can add the 5-bit numbers in Figure 3.2. The required truth table would have 10 input variables, 5 for each number x and y. It would have 210 is equal to 1,024 rows. A better approach is to consider the addition of each pair of bits, 11 and E, separately. For bit position 0, there is no carry-in, and hence the addition is the same as for figure 3.1. For each other bit position I, the addition involves bits 11 and E and a carry in CI, as illustrated in figure 3.2b. This observation leads to the design of a logic circuit that has 3 inputs 11, E, and Ci, and produces the 2 outputs Si and Ci plus 1. The required truth table is shown in figure 3.3a. The sum bit, Si, is the modulo 2 sum of 11, E, and Ci. The carryout, Ci plus 1, is equal to 1 if the sum of 11, E, and Ci is equal to either 2 or 3. Cardinal maps for these functions are shown in part B of the figure. For the carryout function, the optimal sum of products realization is Ci plus 1 equals Xi plus Xi plus Yi. For the Si function, a sum of products realization is Si equals Xi plus Xi plus Xi plus Xi. A more attractive way of implementing this function is by using the XOR gates, as explained below. 3.2 Addition of unsigned numbers Ci 11 ECI plus 1 Si 0 0 0 0 0 0 0 1 0 1 0 1 0 0 1 0 1 1 1 0 1 0 0 0 1 1 0 1 1 0 1 1 0 1 0 1 1 1 1 1 11 ECI 0 1 0 0 0 1 11 10 1 1 1 1 Si equals 11 circle plus E circle plus Ci 0 0 0 1 11 10 0 1 11 ECI 1 1 1 1 1 1 1 1. A. Truth table Ci plus 1 equals 11 E plus sheet C plus Yi. B. Cardinal map Ci 11 ESI Ci 1 plus. C. Circuit figure 3.3 full adder. 128 Number representation and arithmetic circuits CHAPTER3. Use of XOR gates. As shown in Chapter 2, the XOR function of two variables is defined as x1 circle plus x2 equals x1 x2 plus x1 x2. The preceding expression for the sum bit can be manipulated into a form that uses only XOR operations as follows: Si equals Xi plus Xi, Ci plus Xi plus Xi, Ci equals 11 circle plus E, Ci plus 11 circle plus E, Ci equals 11 circle plus E, circle plus Ci. The XOR operation is associative. Hence, we can write Si equals 11 circle plus E circle plus Ci. Therefore, a 3-input XOR operation can be used to realize Si. The XOR operation generates as an output a modulo, 2 sum of its inputs. Thus, the output is equal to 1 if an odd number of inputs have the value 1, and it is equal to 0 otherwise. For this reason, the XOR is sometimes referred to as the odd function. Observe that the XOR has no minterms that can be combined into a larger product term, as evident from the checkerboard pattern for function Si in the map in figure 3.3b. The logic circuit implementing the truth table in figure 3.3a is given in figure 3.3c. This circuit is known as a full adder. Another interesting feature of XOR gates is that a 2-input XOR gate can be thought of as using one input as a control signal that determines whether the true or complemented value of the other input will be passed through the gate as the output value. This is clear from the definition of XOR, where 11 circle plus E equals XY plus XY. Consider X to be the control input. Then, if X equals 0, the output will be equal to the value of Y. But if X equals 1, the output will be equal to the complement of Y. In the derivation above, we used algebraic manipulation to derive Si equals 11 circle plus E circle plus Ci. We could have obtained the same expression immediately by making the following observation. In the top half of the truth table in figure 3.3a, Ci is equal to 0, and the sum function Si is the XOR of 11 and E. In the bottom half of the table, Ci is equal to 1, while Si is the complemented version of its top half. This observation leads directly to our expression using two 2-input XOR operations. We will encounter an important example of using XOR gates to pass true or complemented signals under the control of another signal in section 3.3.3. In the preceding discussion, we encountered the complement of the XOR operation, which we denoted as X circled plus Y. This operation is used so commonly that it is given the distinct name XNOR. A special symbol is often used to denote the XNOR operation, namely XY equals X circled plus Y. The XNOR is sometimes also referred to as the coincidence operation because it produces the output of 1 when its inputs coincide in value. That is, they are both 0 or both 1. 3.2 Addition of unsigned numbers CI-HAS-CSI-S11-HA-CCI plus 1E. A. Block diagram CI-SI-11-ECI plus 1B. Detailed diagram Figure 3.4a. Decomposed implementation of the full adder circuit. 3.2.1 Decomposed full adder. In view of the names used for the circuits, one can expect that a full adder can be constructed using half adders. This can be accomplished by creating a multilevel circuit given in Figure 3.4. It uses two half adders to form a full adder. The reader should verify the functional correctness of the circuit. 3.2.2 Ripple carry adder. To perform addition by hand, we start from the least significant digit and add pairs of digits, progressing to the most significant digit. If a carry is produced in position I, then this carry is added to the operands in position I plus 1. The same arrangement can be used in a logic circuit that performs addition. For each bit position, we can use a full adder circuit connected as shown in Figure 3.5. Note that to be consistent with the customary way of writing numbers, the least significant bit position is on the right. Carries that are produced by the full adders propagate to the left. When the operands X and Y are applied as inputs to the adder, it takes some time before the output sum, S, is valid. Each full adder introduces a certain delay before its SI and CI plus 1 outputs are valid. Let this delay be denoted as T. Thus, the carryout from the first stage, C1, arrives at the second stage T after the application of the X0 and Y0 inputs. The carryout from the second stage, C2, arrives at the third stage with a 2T delay, and so on. The signal Cn-1 is valid after a delay of N-1T, which means that the complete sum is available. 130 Number representation and arithmetic circuits CHAPTER3 checks NYN X1 Y1 X0 Y0 1 to 1 FACN CN1 FAC2 FAC1 C0 SN S1 S0 1 MSB position LSB position Figure 3.5 an N-bit ripple carry adder. After a delay of NT, because of the way the carry signals ripple through the full adder stages, the circuit in Figure 3.5 is called a ripple carry adder. The delay incurred to produce the final sum and carry out in a ripple carry adder depends on the size of the numbers. When 32 or 64-bit numbers are used, this delay may become unacceptably high. Because the circuit in each full adder leaves little room for a drastic reduction in the delay, it may be necessary to seek different structures for implementation of n-bit adders. We will discuss a technique for building high-speed adders in Section 3.4. So far we have dealt with unsigned integers only. The addition of such numbers does not require a carry-in for stage 0. In Figure 3.5 we included C0 in the diagram so that the ripple carry adder can also be used for subtraction of numbers, as we will see in Section 3.3. 3.2.3 Design example. Suppose that we need a circuit that multiplies an 8-bit unsigned number by 3. Let A equals A7 A6 A1 A0 denote the number, and P equals P9 P8. P1 P0 denote the product P equals 3A. Note that 10 bits are needed to represent the product. 2A, 3A. A simple approach to design the required circuit is to use two ripple carry adders to add 3 copies of the number A, as illustrated in Figure 3.6a. The symbol that denotes each adder is a commonly used graphical symbol for adders. The letters 11, E, SI, and CI indicate the meaning of the inputs and outputs according to Figure 3.5. The first adder produces A plus A equals its result is represented as 8 sum bits and the carry from the most significant bit. The second adder produces 2a plus a equals it has to be a 9-bit adder to be able to handle the 9 bits of 2a, which are generated by the first adder. Because the inputs have to be driven only by the 8 bits of a, the 9th input y8 is connected to a constant 0. This approach is straightforward but not very efficient. Because 3a equals 2a plus a, we can observe that 2a can be generated by shifting the bits of a 1-bit position to the left, which gives the bit pattern A7, A6, A5, A4, A3, A2, A1, A0, 0. According to equation 3.1, this pattern is 3.2 addition of unsigned numbers. A7, A0, AX7, X0, Y7, Y0, X7, X0, Y8, Y0, Y7, X8, S0, S7, C7, S0, S8, C8, P9, P8, P0, P3, A equals A naive approach. A7, A0, AX1, X0, Y8, Y0, Y7, X8, S0, S8, C8, 0, 0, P equals 3A. P9, P8, P0. B. Efficient design figure 3.6 circuit that multiplies an 8-bit unsigned number by 3. 132 number representation and arithmetic circuits CHAPTE R3 equal to 2A. Then a single ripple carry adder suffices for implementing 3A as shown in figure 3.6b. This is essentially the same circuit as the second adder in part A of the figure. Note that the input x0 is connected to a constant 0. Note also that in the second adder in part A of the figure the value of x0 is always 0, even though it is driven by the least significant bit, S0, of the sum of the first adder. Because x0 equals y0 equals a0 in the first adder, the sum bit S0 will be 0, whether A0 is 0 or 1. 3.3 Sign numbers. In the decimal system, the sign of a number is indicated by a plus or minus symbol to the left of the most significant digit. In the binary system, the sign of a number is denoted by the leftmost bit. For a positive number, the leftmost bit is equal to 0, and for a negative number, it is equal to 1. Therefore, in sign numbers, the leftmost bit represents the sign, and the remaining n-1 bits represent the magnitude, as illustrated in figure 3.7. It is important to note the difference in the location of the most significant bit, MSB. In unsigned numbers, all bits represent the magnitude of a number, hence all n bits are significant in defining the magnitude. Therefore, the MSB is the leftmost bit, Bn-1. In signed numbers, there are n-1 significant bits, and the MSB is in bit position Bn-2. Bn B1 B0, 1 magnitude MSB, A, and sign number Bn B1 B0, 1 to 2 magnitude sign 0 denotes 1 denotes MSB. B, sign number figure 3.7 formats for representation of integers. 3.3 Sign numbers. 3.3.1 Negative numbers. Positive numbers are represented using the positional number representation as explained in the previous section. Negative numbers can be represented in 3 different ways: sign and magnitude, 1's complement, and 2's complement. Sign and magnitude representation. In the familiar decimal representation, the magnitude of both positive and negative numbers is expressed in the same way. The sign symbol distinguishes a number as being positive or negative. This scheme is called the sign and magnitude number representation. The same scheme can be used with binary numbers, in which case the sign bit is 0 or 1 for positive or negative numbers, respectively. For example, if we use 4-bit numbers, then plus 5 equals 0101 and minus 5 is equal to 1101. Because of its similarity to decimal sign and magnitude numbers, this representation is easy to understand. However, as we will see shortly, this representation is not well suited for use in computers. More suitable representations are based on complementary systems, explained below. 1's complement representation. In a complementary number system, the negative numbers are defined according to a subtraction operation involving positive numbers. We will consider 2 schemes for binary numbers: the 1's complement and the 2's complement. In the ones complement scheme, an n-bit negative number, k, is obtained by subtracting its equivalent positive number, p, from 2n-1, that is, k equals 2n-1 minus p. For example, if n equals 4, then k equals 24 minus 1 minus p equals 15, 10 minus p equals 11, 11, 2 minus p. If we convert plus 5 to a negative, we get minus 5 is equal to 1111 minus 0, 101 equals 1010. Similarly, plus 3 equals 0011, and minus 3 is equal to 1111 minus 0011 equals 1100. Clearly, the ones complement can be obtained simply by complementing each bit of the number, including the sign bit. While ones complement numbers are easy to derive, they have some drawbacks when used in arithmetic operations, as we will see in the next section. Two's complement representation. In the two's complement scheme, a negative number, k, is obtained by subtracting its equivalent positive number, p, from 2n, namely, k equals 2n minus p. Using our 4-bit example, minus 5 is equal to 10,000 minus 0101 equals 1011, and minus 3 is equal to 10,000 minus 0011 equals 1101. Finding two's complements in this manner requires performing a subtraction operation that involves borrows. However, we can observe that if k1 is the ones complement of p and k2 is the two's complement of p, then 2n minus k1 equals 1, minus pk2 equals 2 and minus p. It follows that k2 equals k1 plus 1. Thus, a simpler way of finding a two's complement of a number is to add 1 to its ones complement, because finding a ones complement is trivial. This is how two's complement numbers are obtained in logic circuits that perform arithmetic operations. The reader will need to develop an ability to find two's complement numbers quickly. There is a simple rule that can be used for this purpose. 134 number representation and arithmetic circuits, CHAPTER3 rule for finding two's complements. Given a number b equals bn minus 1 bn minus 2, b1 b0, its two's complement, k equals kn minus 1 kn minus 2, k1 k0, can be found by examining the bits of b from right to left and taking the following action. Copy all bits of b that are 0 and the first bit that is 1, then simply complement the rest of the bits. For example, if b equals 0, 1, 1, 0, then we copy k0 equals b0 equals 0 and k1 equals b1 equals 1, and complement the rest so that k2 equals b2 equals 0 and k3 equals b3 equals 1. Hence, k equals 1010. As another example, if b equals 10110100, then k equals 01001100. We leave the proof of this rule as an exercise for the reader. Table 3.2 illustrates the interpretation of all 16 4-bit patterns in the 3-sig number presentations that we have considered. Note that for both sign and magnitude representation and for ones complement representation, there are 2 patterns that represent the value 0. For two's complement, there is only one such pattern. Also, observe that the range of numbers that can be represented with 4 bits in two's complement form is -8 to +7, while in the other 2 representations it is -7 to +7. Using two's complement representation, an n-bit number b equals bn minus 1 bn minus 2. b1 b0 represents a value 2n minus 1. 2n minus 2 plus 21 plus 20 b equals minus bn minus 1 times plus bn minus 2 times plus b1 times b0 times 3.2. Thus, the largest negative number 100, 0, has the value minus 2 and minus 1. The largest positive number, 0, 11, has the value 2 and minus 1 minus 1. Table 3.2 interpretation of 4-bit signed integers. Sign and b3, b2, b1, b0 magnitude, ones complement, two's complement. 0 1 1 1 plus 7 plus 6 plus 7 plus 6 plus 7 plus 6 0 1 1 0 plus 5 plus 5 plus 5 0 1 0 1 plus 4 plus 4 plus 4 0 100 plus 3 plus 3 plus 3 0 0 1 1 plus 2 plus 2 plus 2 0 0 1 0 plus 1 plus 1 plus 1 0 0 0 1 plus 0 plus 0 plus 0 0 0 0 0 minus 0 minus 7 minus 8 1000 minus 1 minus 6 minus 7 1000 1 minus 2 minus 5 minus 6 1000 10 minus 3 minus 4 minus 5 1000 11 minus 4 minus 3 minus 4 1100 minus 5 minus 2 minus 3 1101 minus 6 minus 1 minus 2 11 10 minus 7 minus 0 minus 1 11 11. 3.3 Sign numbers, 3.3.2 Addition and subtraction. To assess the suitability of different number representations, it is necessary to investigate their use in arithmetic operations, particularly in addition and subtraction. We can illustrate the good and bad aspects of each representation by considering very small numbers. We will use 4-bit numbers, consisting of a sign bit and 3 significant bits. Thus, the numbers have to be small enough so that the magnitude of their sum can be expressed in 3 bits, which means that the sum cannot exceed the value 7. Addition of positive numbers is the same for all 3 number representations. It is actually the same as the addition of unsigned numbers discussed in section 3.2. But there are significant differences when negative numbers are involved. The difficulties that arise become apparent if we consider operands with different combinations of signs. Sign and magnitude addition. If both operands have the same sign, then the addition of sign and magnitude numbers is simple. The magnitudes are added, and the resulting sum is given the sign of the operands. However, if the operands have opposite signs, the task becomes more complicated. Then it is necessary to subtract the smaller number from the larger one. This means that logic circuits that compare and subtract numbers are also needed. We will see shortly that it is possible to perform subtraction without the need for this circuitry. For this reason, the sign and magnitude representation is not used in computers. Ones complement addition. An obvious advantage of the ones complement representation is that a negative number is generated simply by complementing all bits of the corresponding positive number. Figure 3.8 shows what happens when 2 numbers are added. There are 4 cases to consider in terms of different combinations of signs. As seen in the top half of the figure, the computation of 5 plus 2 is equal to 7 and minus 5 plus 2 equals minus 3 is straightforward. A simple addition of the operands gives the correct result. Such is not the case with the other 2 possibilities. Computing 5 plus minus 2 equals 3 produces the bit vector 1 0 0 1 0. Because we are dealing with 4-bit numbers, there is a carryout from the sign bit position. Also, the 4 bits of the plus 5, 0 1 0 1, minus 5, 1 0 1 0, plus 2, plus 0 0 1 0, plus 2, plus 0 0 1 0, plus 7, 0 1 1 1, minus 3, 1 1 0 0 plus 5 plus minus 2, 0 1 0 1 1 1 0 1 plus minus 5 plus minus 2, 1 0 1 0 1 1 0 1 plus 3, 0 0 1 0 1 1 1 minus 7, 0 1 1 1 1 0 0 1 1 1 0 0 0. Figure 3.8 examples of ones complement addition. 136 Number representation and arithmetic circuits, CHAPTER3. Result represent the number 2 rather than 3, which is a wrong result. Interestingly, if we take the carryout from the sign bit position and add it to the result in the least significant bit position, the new result is the correct sum of 3. This correction is indicated in blue in the figure. A similar situation arises when adding minus 5 plus minus 2 equals minus 7. After the initial addition, the result is wrong because the 4 bits of the sum are 0 1 1 1, which represents plus 7 rather than minus 7. But again, There is a carryout from the sign bit position, which can be used to correct the result by adding it in the LSB position, as shown in figure 3.8. The conclusion from these examples is that the addition of one's complement numbers may or may not be simple. In some cases, a correction is needed, which amounts to an extra addition that must be performed. Consequently, the time needed to add two one's complement numbers may be twice as long as the time needed to add two unsigned numbers. 2's complement addition. Consider the same combinations of numbers as used in the one's complement example. Figure 3.9 indicates how the addition is performed using 2's complement numbers. Adding 5 plus 2 is equal to 7 and minus 5 plus 2 equals minus 3 is straightforward. The computation 5 plus minus 2 equals 3 generates the correct 4 bits of the result, namely 0, 0, 1, 1. There is a carryout from the sign bit position, which we can simply ignore. The fourth case is minus 5 plus minus 2 equals minus 7. Again, the 4 bits of the result, 1001, give the correct sum, minus 7. In this case also, the carryout from the sign bit position can be ignored. As illustrated by these examples, the addition of 2's complement numbers is very simple. When the numbers are added, the result is always correct. If there is a carryout from the sign bit position, it is simply ignored. Therefore, the addition process is the same, regardless of the signs of the operands. It can be performed by an adder circuit, such as the one shown in figure 3.5. Hence, the 2's complement notation is highly suitable for the implementation of addition operations. We will now consider its use in subtraction operations. Plus 5, 0, 1, 0, 1 minus 5, 1, 0, 1, 1 plus 2, plus 0, 0, 1, 0, plus 2, plus 0, 0, 1, 0, plus 7, 0, 1, 1, 1, minus 3, 1, 1, 0, 1 plus 5, 0, 1, 0, 1, minus 5, 1, 0, 1, 1 plus, minus 2, 1, 1, 1, 0 plus, minus 2, 1, 1, 1, 0, plus 3, 0, 0, 1, 1, 1, minus 7, 1, 0, 0, 1, 1. Ignore figure 3.9 examples of 2's complement addition. 3.3 Sign numbers 2's complement subtraction. The easiest way of performing subtraction is to negate the subtrahend and add it to the minuend. This is done by finding the 2's complement of the subtrahend and then performing the addition. Figure 3.10 illustrates the process. The operation 5 minus plus 2 equals 3 involves finding the 2's complement of plus 2, which is 1110. When this number is added to 0101, the result is 0011 equals plus 3, and a carryout from the sign bit position occurs, which is ignored. A similar situation arises for minus 5 minus plus 2 equals minus 7. In the remaining two cases, there is no carryout, and the result is correct. As a graphical aid to visualize the addition and subtraction examples in figures 3.9 and 3.10, we can place all possible 4-bit patterns on a modulo 16 circle given in figure 3.11a. If these bit patterns represented unsigned integers, they would be numbers 0 to 15. If they represent 2's complement integers, then the numbers range from minus 8 to plus 7, as shown. The addition operation is done by stepping in the clockwise direction by the magnitude of the number to be added. For example, minus 5 plus 2 is determined by starting at 1011 equals minus 5 and moving clockwise 2 steps, giving the result 1101 equals minus 3. Figure 3.11b shows how subtraction can be performed on the modulo 16 circle using the example 5 minus 2 is equal to 3. We can start at 0101 equals plus 5 and move counterclockwise by 2 steps, which gives 0011 equals plus 3. But we can also use the 2's complement of 2 and add this value by stepping in the clockwise. Plus 5, 010101012, 0010 plus 1110 plus 3, 10011 ignore, minus 5, plus 2, 1 0 1 1 0 0 1 0 plus 1 0 1 1 1 1 1 0, minus 7, 1 1 0 0 1 ignore, plus 5, 0 1 0 1 0 1 0 1, minus 2, 1 1 1 0 plus 7, 0 0 1 0 0 1 1 1 1 0 1 1, minus 5, 1 0 1 1, minus 2, 1 1 1 0 plus 0 0 1 0, minus 3, 1 1 0 1. Figure 3.10 Examples of 2's complement subtraction. 138 Number representation and arithmetic circuits CHAPTE are 3 to 0 0 0 0, 1 1 1 1, 0 0 0 1, 1 1 1 0 0 0 1 0, 1 1 0 1, 0 0 1 1, 1 1 0 0, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1 1 0 0 0, 1 0 0 1, 1 0 1 0 minus 1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 to 2, 3 to 4, 5 to 6, 7 to 8 0 1011. 0 0 0 0, 0 0 0 1, 0 0 1 0, 0 0 1 1 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1 1 0 0 0, 1 0 0 1, 1 0 1 0, 1 0 1 1 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1 1 plus 1, 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 2, 3, 4, 5, 6, 7, 8, 0. Subtract 2, add 16 minus 2 is equal to 14. A. The number circle. B. Subtracting 2 by adding its 2's complement. Figure 3.11 Graphical interpretation of 4-bit 2's complement numbers. Direction as shown in the figure. Since there are 16 numbers on the circle, the value we need to add is 16 minus 2 equals 14, 10 equals 11, 10, 2. The key conclusion of this section is that the subtraction operation can be realized as the addition operation, using a 2's complement of the subtrahend, regardless of the signs of the two operands. Therefore, it should be possible to use the same adder circuit to perform both addition and subtraction. 3.3.3 Adder and subtractor unit. The only difference between performing addition and subtraction is that for subtraction it is necessary to use the 2's complement of one operand. Let x and y be the two operands, such that y serves as the subtrahend in subtraction. From section 3.3.1 we know that a 2's complement can be obtained by adding 1 to the 1's complement of y. Adding 1 in the least significant bit position can be accomplished simply by setting the carry-in bit C0 to 1. A 1's complement of a number is obtained by complementing each of its bits. This could be done with NOT gates, but we need a more flexible circuit where we can use the true value of y for addition and its complement for subtraction. In section 3.2 we explained that two-input XOR gates can be used to choose between true and complemented versions of an input value under the control of the other input. This idea can be applied in the design of the adder/subtractor unit as follows. Assume that there exists a control signal that chooses whether addition or subtraction is to be performed. Let 3.3 Sign numbers yn, y1, y0, 1 add/sub control C0, xn, x1, x0, 1 n-bit adder sn, s1, s0, 1 cn. Figure 3.12 Adder/subtractor unit. This signal be called add/sub. Also, let its value be 0 for addition and 1 for subtraction. To indicate this fact, we placed a bar over add. This is a commonly used convention, where a bar over a name means that the action specified by the name is to be taken if the control signal has the value 0. Now, let each bit of y be connected to one input of an XOR gate, with the other input connected to add/sub. The outputs of the XOR gates represent y if add/sub equals 0, and they represent the 1's complement of y if add/sub equals 1. This leads to the circuit in figure 3.12. The main part of the circuit is an n-bit adder, which can be implemented using the ripple carry structure of figure 3.5. Note that the control signal add/sub is also connected to the carry in C0. This makes C0 equals 1 when subtraction is to be performed, thus adding the 1 that is needed to form the 2's complement of y. When the addition operation is performed, we will have C0 equals 0. The combined adder/subtractor unit is a good example of an important concept in the design of logic circuits. It is useful to design circuits to be as flexible as possible and to exploit common portions of circuits for as many tasks as possible. This approach minimizes the number of gates needed to implement such circuits, and it reduces the wiring complexity substantially. 3.3.4 Radix complement schemes * operator. The 2's complement scheme is just a special case of radix complement schemes which we discuss in this section. This general discussion can be skipped without loss of continuity in the context of computer technology. 140 Number representation and arithmetic circuits, CHAPTER3. The idea of performing a subtraction operation by addition of a complement of the subtrahend is not restricted to binary numbers. We can gain some insight into the workings of the 2's complement scheme by considering its counterpart in the decimal number system. Consider the subtraction of two-digit decimal numbers. Computing a result such as 74 minus 33 is equal to 41 is simple because each digit of the subtrahend is smaller than the corresponding digit of the minuend. Therefore, no borrow is needed in the computation. But computing 74 minus 36 is equal to 38 is not as simple, because a borrow is needed in subtracting the least significant digit. If a borrow occurs, the computation becomes more complicated. Suppose that we restructure the required computation as follows: 74 minus 36 is equal to 74 plus 100 minus 100 minus 36 is equal to 74 plus 100 minus 36 minus 100. Now two subtractions are needed. Subtracting 36 from 100 still involves borrows. But noting that 100 is equal to 99 plus 1, these borrows can be avoided by writing 74 minus 36 is equal to 74 plus 99 plus 1 minus 36 minus 100 is equal to 74 plus 99 minus 36 plus 1 minus 100. The subtraction in parentheses does not require borrows. It is performed by subtracting each digit of the subtrahend from 9. We can see a direct correlation between this expression and the one used for 2's complement, as reflected in the circuit in figure 3.12. The operation 99 minus 36 is analogous to complementing the subtrahend y to find its 1's complement, which is the same as subtracting each bit from 1. Using decimal numbers, we find the 9's complement of the subtrahend by subtracting each digit from 9. In figure 3.12 we add the carry-in of 1 to form the 2's complement of y. In our decimal example we perform 99 minus 36 plus 1 is equal to 64. Here 64 is the 10's complement of 36. For an n-digit decimal number, n, its 10's complement, k10, is defined as k10 equals 10 n minus n, while its 9's complement, k9, is k9 equals 10 n minus 1 minus n. Thus the required subtraction, 74 minus 36, can be performed by addition of the 10's complement of the subtrahend, as in 74 minus 36 is equal to 74 plus 64 minus 100 is equal to 138 minus 100 is equal to 38. The subtraction 138 minus 100 is trivial because it means that the leading digit in 138 is simply deleted. This is analogous to ignoring the carryout from the circuit in figure 3.12, as discussed for the subtraction examples in figure 3.10. Example 3.1: suppose that a and b are n-digit decimal numbers. Using the above 10's complement approach, b can be subtracted from a as follows: minus a minus b equals a plus 10nb minus 10n. If a minus greater than or equal to b, then the operation a plus 10nb produces a carryout of 1. This carry is equivalento 10n, hence it can be simply ignored. 3.3 sign numbers 141, but if A less than B, then the operation A plus 10 n minus B produces a carryout of 0. Let the result obtain Bm so that A minus B equals m minus 10, and we can rewrite this as 10 n minus B minus A equals m. The left side of this equation is the tens complement of B minus A. The tens complement of a positive number represents a negative number that has the same magnitude. Hence, m correctly represents the negative value obtained from the computation A minus B when A less than B. This concept is illustrated in the examples that follow. When dealing with binary sign numbers, we use 0 in the leftmost bit position to denote a positive number and 1 to denote a negative number. If we wanted to build hardware that operates on signed decimal numbers, we could use a similar approach. Let 0 in the leftmost digit position denote a positive number and let 9 denote a negative number. Note that 9 is the 9's complement of 0 in the decimal system, just as 1 is the 1's complement of 0 in the binary system. Thus, using 3-digit sign numbers A equals 0.45 and B equals 0.27 are positive numbers with magnitudes 45 and 27, respectively. The number B can be subtracted from A as follows. Example 3.2. A minus B equals 0.45 minus 0.27 equals 0.45 plus 1,000 to 1,000 minus 0.27 equals 0.45 plus 999 minus 0.27 plus 1 minus 1,000 equals 0.45 plus 972 plus 1 minus 1,000 is equal to 1,018 minus 1,000 equals 0.18. This gives the correct answer of plus 18. Next, consider the case where the minuend has lower value than the subtrahend. This is illustrated by the computation B minus A equals 0.27 minus 0.45 equals 0.27 plus 1,000. Minus 1,000 minus 0.45 equals 0.27 plus 999 minus 0.45 plus 1 minus 1,000 equals 0.27 plus 954 plus 1 minus 1,000 is equal to 982 minus 1,000. From this expression, it appears that we still need to perform the subtraction 982 minus 1,000. But as seen in example 3.1, this can be rewritten as 982 is equal to 1,000 plus B minus A equals 1,000 minus A minus B. 142 Number Representation and Arithmetic Circuits, CHAPTER3. Therefore, 982 is the negative number that results when forming the tens complement of A minus B. From the previous computation, we know that A minus B equals 0.18, which denotes plus 18. Thus, the sign number 982 is the tens complement representation of minus 18, which is the required result. These examples illustrate that sign numbers can be subtracted without using a subtraction operation that involves borrows. The only subtraction needed is in forming the 9's complement of the subtrahend, in which case each digit is simply subtracted from 9. Thus, a circuit that forms the 9's complement, combined with a normal adder circuit, will suffice for both addition and subtraction of decimal sign numbers. A key point is that the hardware needs to deal only with n digits if n-digit numbers are used. Any carry that may be generated from the leftmost digit position is simply ignored. The concept of subtracting a number by adding its radix complement is general. If the radix is r, then the r's complement, kr, of an n-digit number, n, is determined as kr equals rn minus n. The r minus 1 s complement, kr minus 1, is defined as kr minus 1 equals rn minus 1 minus n. It is computed simply by subtracting each digit of n from the value r minus 1. The r minus 1 s complement is referred to as the diminished radix complement. Circuits for forming the r minus 1 s complements are simpler than those for general subtraction that involves borrows. The circuits are particularly simple in the binary case, where the 1's complement requires just inverting each bit. Example 3.3 in Figure 3.10 we illustrated the subtraction operation on binary numbers given in 2-foot complement representation. Consider the computation plus 5 minus plus 2 equals plus 3 using the approach discussed above. Each number is represented by a 4-bit pattern. The value 24 is represented as 10,000. Then 0101 to 0010 equals 0101 plus 10,000 minus 0010 minus 10,000 equals 0101 plus 1111 to 0010 plus 1 minus 10,000 equals 0101 plus 1101 plus 1 minus 10,000 is equal to 10,000, and 11 minus 10,000 equals 0011. Because 5 greater than 2, there is a carry from the 4th bit position. It represents the value 24, denoted by the pattern 10,000. Example 3.4. Consider now the computation plus 2 minus plus 5 equals minus 3, which gives minus equals plus minus minus. 001001010010 10000 0101 10,000 equals 0010 plus 1111 to 0101 plus 1 minus 10,000 equals 0010 plus 1,010 plus 1 minus 10,000 is equal to 1,101 minus 10,000. 3.3 Sign numbers 143. Because 2 less than 5, there is no carry from the 4th bit position. 2's complement representation of minus 3. Note that equals plus minus the answer, 1101, is the 1101, 10000, 00100101 equals 10,000 minus 0101 to 0010 equals 10,000 minus 0011, indicating that 1101 is the 2's complement of 0011 plus 3. Finally, consider the case where the subtrahend is a negative number. The computation plus 5 minus 2 equals plus 7 is done as follows: minus equals plus minus minus. Example 3.5. 0101 1110 0101 100 001110 10,000 equals 0101 plus 1111 to 1110 plus 1 minus 10,000 equals 0101 plus 0001 plus 1 minus 10,000 equals 0111 minus 10,000. While 5 minus 2, the pattern 1110 is greater than the pattern 0101 when the patterns are treated as unsigned numbers. Therefore, there is no carry from the 4th bit position. The answer 0111 is the 2's complement representation of plus 7. Note that equals plus minus 0111, 10000, 0101 1110 is equal to 10,000 minus 1110 to 0101 equals 10,000 minus 1,001, and 1,001 represents minus 7. 3.3.5 Arithmetic overflow. The result of addition or subtraction is supposed to fit within the significant bits used to represent the numbers. If n bits are used to represent signed numbers, then the result must be in the range minus 2 and minus 1 to 2 and minus 1 minus 1. If the result does not fit in this range, then we say that arithmetic overflow has occurred. To ensure the correct operation of an arithmetic circuit, it is important to be able to detect the occurrence of overflow. Figure 3.13 presents the 4 cases where 2's complement numbers with magnitudes of 7 and 2 are added. Because we are using 4-bit numbers, there are 3 significant bits, b2 minus 0. When the numbers have opposite signs, there is no overflow. But if both numbers have the same sign, the magnitude of the result is 9, which cannot be represented with just 3 significant bits. Therefore, overflow occurs. The key to determining whether overflow occurs is the carryout from the MSB position, called C3 in the figure, and from the sign bit position, called C4. The figure indicates that overflow occurs when these carryouts have different values, and a correct sum is produced when they have the same value. Indeed, this is true in general for both addition and subtraction of 2's complement numbers. As a quick 144 number representation and arithmetic circuits CHAPTER3 plus 7 plus 2 plus 0 1 1 1 0 0 1 0 plus 2 minus 7 plus 1 0 0 1 0 0 1 0 plus 9 1 0 0 1 minus 5 1 0 1 1 C4 equals 0 C3 equals 1 C4 equals 0 C3 equals 0 7 0 1 1 1 minus 7 1 0 0 1 plus minus 2 plus 1 1 1 0 plus minus 2 plus 1 1 1 0 minus 9 C4 equals 1 C4 equals 1 C3 equals 1 C3 equals 0 plus 0 1 5 0 1 0 1 1 1 1 1 Figure 3.13 Examples for determination of overflow. Check of this statement. Consider the examples in Figure 3.9 where the numbers are small enough so that overflow does not occur in any case. In the top two examples in the figure, there is a carryout of 0 from both sign and MSB positions. In the bottom two examples, there is a carryout of 1 from both positions. Therefore, for the examples in Figures 3.9 and 3.13, the occurrence of overflow is detected by overflow equals C3 C4 plus C3 C4 equals C3 circle plus C4. For n-bit numbers, we have overflow equals Cn minus 1 circle plus Cn. Thus, the circuit in Figure 3.12 can be modified to include overflow checking with the addition of one XOR gate. An alternative and more intuitive way of detecting the arithmetic overflow is to observe that overflow occurs if both summands have the same sign but the resulting sum has a different sign. Let x equals x3 x2 x1 x0 and y equals y3 y2 y1 y0 represent 4-bit 2's complement numbers, and let s equals s3 s2 s1 s0 be the sum s equals x plus y. Then overflow equals x3 y3 s3 plus x3 y3 s3. The carryout and overflow signals indicate whether the result of a given addition is too large to fit into the number of bits available to represent the sum. The carryout is meaningful only when unsigned numbers are involved, while the overflow is meaningful only in the case of signed numbers. In a typical computer, it is prudent to use the same adder circuits for dealing with both unsigned and signed operands, thus reducing the amount of circuitry required. This means that both the carryout and overflow signals should be generated as 3.4 fast adders. We have discussed. Then, a program instruction that specifies unsigned operands can use the carryout signal, while an instruction that has signed operands can use the overflow signal. 3.3.6 Performance issues. When buying a digital system, such as a computer, the buyer pays particular attention to the performance that the system is expected to provide and to the cost of acquiring the system. Superior performance usually comes at a higher cost. However, a large increase in performance can often be achieved at a modest increase in cost. A commonly used indicator of the value of a system is its price/performance ratio. The addition and subtraction of numbers are fundamental operations that are performed frequently in the course of a computation. The speed with which these operations are performed has a strong impact on the overall performance of a computer. In light of this, let us take a closer look at the speed of the adder/subtractor unit in Figure 3.12. We are interested in the largest delay from the time the operands x and y are presented as inputs until the time all bits of the sum s and the final carryout, Cn, are valid. Most of this delay is caused by the n-bit adder circuit. Assume that the adder is implemented using Therapel-Kara structure in Figure 3.5 and that each full adder stage is the circuit in Figure 3.3c. The delay for the carryout signal in this circuit, T, is equal to 2 gate delays. From section 3.2.2 we know that the final result of the addition will be valid after a delay of nt, which is equal to 2 n-gate delays. In addition to the delay in the Ripple-Carry path, there is also a delay in the XOR gates that feed either the true or complemented value of y to the adder inputs. If this delay is equal to 1 gate delay, then the total delay of the circuit in Figure
3.12 is 2 or 1 grote delays.
For a large n, say n equals 32 or n equals 64, The delay would lead to unacceptably poor performance. Therefore, it is important to find faster circuits to perform addition. The speed of any circuit is limited by the longest delay along the paths through the circuit. In the case of the circuit in Figure 3.12, the longest delay is along the path from the input through the XOR gate and through the carry circuit of each adder stage. The longest delay is often referred to as the critical path delay, and the path that causes this delay is called the critical path. 3.4 Fast adders. The performance of a large digital system is dependent on the speed of circuits that form its various functional units. Obviously, better performance can be achieved using faster circuits. This can be accomplished by using superior, usually newer, technology in which the delays in basic gates are reduced. But it can also be accomplished by changing the overall structure of a functional unit, which may lead to even more impressive improvement. In this section, we will discuss an alternative for implementation of an n-bit adder, which substantially reduces the time needed to add numbers. 146 Number representation and arithmetic circuits CHAPTER 3.4.1 Carry-Lucas adder. To reduce the delay caused by the effect of carry propagation through the ripple carry adder, we can attempt to evaluate quickly for each stage whether the carry-in from the previous stage will have a value 0 or 1. If a correct evaluation can be made in a relatively short time, then the performance of the complete adder will be improved. From Figure 3.3b, the carry-out function for stage I can be realized as Ci plus 1 equals Xi plus Xi plus Yi. If we factor this expression as Ci plus 1 equals Xi plus 11 plus E Ci, then it can be written as Ci plus 1 equals Gi plus pi Psi 3.3, where Gi equals Xi pi equals 11 plus E. The function Gi is equal to 1 when both inputs 11 and E are equal to 1, regardless of the value of the incoming carry to this stage, Ci. Since in this case stage I is guaranteed to generate a carryout, G is called the generate function. The function pi is equal to 1 when at least one of the inputs 11 and E is equal to 1. In this case, a carryout is produced if Ci equals 1. The effect is that the carry-in of 1 is propagated through stage I, hence pi is called the propagate function. Expanding the expression 3.3 in terms of stage I minus 1 gives Ci plus 1 equals Gi plus pi, Gi minus 1 plus pi minus 1 Ci minus 1. Equals Gi plus Pg minus 1 plus Pp minus 1 Ci minus 1. The same expansion for other stages, ending with stage 0, gives Ci plus 1 equals Gi plus Pg minus 1 plus Pp minus 1 Gi minus 2 plus Pp minus 1 P2 P1 G0 plus Pp minus 1 P1 P0 C0, 3.4. This expression represents a two-level AND/OR circuit in which Ci plus 1 is evaluated very quickly. An adder based on this expression is called a carry-Lucas adder. To appreciate the physical meaning of expression 3.4, it is instructive to consider its effect on the construction of a fast adder in comparison with the details of therapal carry adder. We will do so by examining the detailed structure of the two stages that add the least significant bits, namely stages 0 and 1. Figure 3.14 shows the first two stages of a ripple carry adder in which the carryout functions are implemented as indicated in expression 3.3. Each stage is essentially the circuit from Figure 3.3c except that an extra OR gate is used, which produces the pi signal instead of ON and gate because we factored the sum of products expression for Ci plus 1. 3.4 Fast adders X1 Y1 X0 Y0 G1 P1 stage 1 G0 P0 stage 0 C0 C1 C2 S1 S0 Figure 3.14 A ripple carry adder based on expression 3.3. The slow speed of the ripple carry adder is caused by the long path along which a carry signal must propagate. In Figure 3.14, the critical path is from inputs X0 and Y0 to the output C2. It passes through 5 gates, as highlighted in blue. The path in other stages of an n-bit adder is the same as in stage 1. Therefore, the total number of gate delays along the critical path is 2n+1. Figure 3.15 gives the first two stages of the Carey-Lucas adder, using expression 3.4 to implement the carry-out functions. Thus, C1 equals G0 plus P0 C0, C2 equals G1 plus P1 G0 plus P1 P0 C0. This circuit does not have the long ripple carry path that is present in figure 3.14. Instead, all carry signals are produced after 3 gate delays. 1 gate delay is needed to produce the generate and propagate signals G0, G1, P0, and P1, and 2 more gate delays are needed to produce C1 and C2 concurrently, extending the circuit to n bits, the final carryout signal. 148 number representation and arithmetic circuits CHAPTER3 text 1Y1 X0 Y0 C0 C2 G1 P1 S1 S0 C1 G0 P0 Figure 3.15 the first 2 stages of a Carey-Lucas adder. Cn would also be produced after only 3 gate delays because expression 3.4 is just a large 2-level AND/OR circuit. The total delay in the n-bit Carey-Lucas adder is 4 gate delays. The values of all GI and pi signals are determined after 1 gate delay. It takes 2 more gate delays to evaluate all carry signals. Finally, it takes 1 more gate delay XOR to generate all sum bits. The key to the good performance of the adder is quick evaluation of carry signals. The complexity of an n-bit Carey-Lucas adder increases rapidly as n becomes larger.
The complexity of an n-bit Carey-Lucas adder increases rapidly.
The complexity of an n-bit Carey-Lucas adder increases rapidly as n becomes larger. To reduce the complexity, we can use a hierarchical approach in designing large adders. Suppose that we want to design a 32-bit adder. We can divide this adder into 4 8-bit blocks, such that block 0 adds bit 7. 0, block 1 adds bits 15. 8. Block 2 adds bits 23. 16 and block 3 adds bits 31. 24. Then we can implement each block as an 8-bit Carey-Lucas adder. The carryout signals from the 4 blocks are C8, C16, C24. 3.4 fast adders X31, Y31, X15, Y15, 24 to 24, 8 to 8. 0 to 0 X7 Y7 block 32 C24 C16 C8 C0 3 block 1 block 0 S31 S15 24 to 8 0 S7. Figure 3.16 a hierarchical Carey-Lucas adder with ripple carry between blocks. And C32. Now we have 2 possibilities. We can connect the 4 blocks as 4 stages in a ripple carry adder. Thus, while Carey-Lucas head is used within each block, the carries ripple between the blocks. This circuit is illustrated in Figure 3.16. Instead of using a ripple carry approach between blocks, a faster circuit can be designed in which a second-level Carey-Lucas head is performed to produce quickly the carry signals between blocks. The structure of this hierarchical Carey-Lucas adder is shown in Figure 3.17. Each block in the top row includes an 8-bit Carey-Lucas adder, based on generate and propagate signals for each stage in the block, as discussed before. However, instead of producing a carryout signal from the most significant bit of the block, each block produces generate and propagate signals for the entire block. Let Gj and Pj denote these signals for each block J. Now Gj and Pj can be used as inputs to a second-level Carey-Lucas circuit at the bottom of Figure 3.17, which evaluates all carries between blocks. We can derive the block generate and propagate signals for block 0 by examining the expression for C8.
8 võrdub 7 pluss 7 gramm 6 pluss 7 6 gramm.
C8 equals G7 plus P7 G6 plus P7 P6 G5 plus P7 P6 P5 G4 plus P7 P6 P5 P4 G3 plus P7 P6 P5 P4 P3 G2 plus P7 P6 P5 P4 P3 P2 G1 plus P7 P6 P5 P4 P3 P2 P1 G0 plus P7 P6 P5 P4 P3 P2 P1 P0 C0. The last term in this expression specifies that, if all 8 propagate functions are 1, then the carry in C0 is propagated through the entire block. Hence P0 equals P7 P6 P5 P4 P3 P2 P1 P0. The rest of the terms in the expression for C8 represent all other cases when the block produces a carryout. Thus G0 equals G7 plus P7 G6 plus P7 P6 G5 plus P7 P6 P5 P4 P3 P2 P1 G0. The expression for C8 in the hierarchical adder is given by C8 equals G0 plus P0 C0. For block 1 the expressions for G1 and P1 have the same form as for G.
For block 1 the expressions for G1 and P1 have the same form as for G0 and P0 except that each subscript I is replaced by I plus 8. The expressions for G2, P2, G3, and P3 are derived in 150 number representation and arithmetic circuits CHAPTER3 text 31 Y31 X15 Y15 24 to 24 8 to 8 0 to 0 X7 Y7 Block 3 Block 1 Block 0 Second Level Look Ahead C0 S70 P0 G0 P1 G1 P3 G3 S15 8 S31 24 C8 C16 C32 C24 Figure 3.17 A hierarchical carry look ahead adder. The same way, the expression for the carryout of block 1 C16 is C16 equals G1 plus P1 C8 equals G1 plus P1 G0 plus P1 P0 C0. Similarly, the expressions for C24 and C32 are 24 võrdub 2 pluss 21 pluss
C24 equals G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0 C32 equals G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P3 P2 P1 P0 C0. Using this scheme, it takes two more
gate delays to produce the carry signals C8, C16, C24, and C32 than the time needed to generate the GJ and PJ functions. Therefore, since GJ and PJ require 3 gate delays, C8, C16, C24, and C32 are available after 5 gate delays. The time needed to add 2 32-bit numbers involves these 5 gate delays plus 2 more to produce the internal carries in blocks 1, 2, and 3, plus 1 more gate delay, XOR, to generate each sum bit. This gives a total of 8 gate delays. In section 3.3.6 we determined that it takes 2n plus 1 gate delays to add 2 numbers using a ripple carry adder. For 32-bit numbers this implies 65 gate delays. It is clear that the carry look ahead adder offers a large performance improvement. The trade-off is much greater complexity of the required circuit. 3.5 Design of arithmetic circuits using CAD tools technology considerations. C 3.5 Because go ahead. The preceding delay technology considerations. The preceding delay analysis assumes that gates with any number of inputs can be used. But the number of gate inputs, referred to as the fan-in of the gate, has to be limited in practice as we discuss in Appendix B. Therefore, the reality of fan-in constraints must be taken into account. To illustrate this problem, Consider the expressions for the first 8 carries. C1 equals G0 plus P0 C0, C2 equals G1 plus P1 G0 plus P1 P0 C0. 8 võrdub 7 pluss 7 gramm 6 pluss 7 6.
C8 equals G7 plus P7 G6 plus P7 P6 G5 plus P7 P6 P5 G4 plus P7 P6 P5 P4 G3 plus P7 P6 P5 P4 P3 G2 plus P7 P6 P5 P4 P3 P2 G1 plus P7 P6 P5 P4 P3 P2 P1 G0 plus P7 P6 P5 P4 P3 P2 P1 P0 C0. Suppose that the maximum fan-in of the gates is 4 inputs. Then it is impossible.
Suppose that the maximum fan-in of the gates is 4 inputs. Then it is impossible to implement all of these expressions with a 2-level AND/OR circuit. The biggest problem is C8, where one of the AND gates requires 9 inputs. Moreover, the OR gate also requires 9 inputs. To meet the fan-in constraint, we can rewrite the expression for C8 as 8 võrdub 7 pluss 7 gramm 6 pluss 7 6 gramm 5 pluss 7.
C8 equals G7 plus P7 G6 plus P7 P6 G5 plus P7 P6 P5 G4 plus P7 P6 P5 P4 G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 G0 plus P7 P6 P5 P4 P3 P2 P1 P0 C0. To implement this expression we need 10 AND gates and 3 OR gates. The propagation delay in generating C8 consists of 1 gate delay to develop all Gi and Pi, 2 gate delays to produce the sum of products terms in parentheses, 1 gate delay to form the product term in square brackets, and 1 delay for the final O-ring of terms. Hence C8 is valid after 5 gate delays, rather than the 3 gate delays that would be needed without the fan-in constraint. Because fan-in limitations reduce the speed of the carry-loop head adder, some devices that are characterized by low fan-in include dedicated circuitry for implementation of fast adders. Examples of such devices include FPGAs, which are described in Appendix B 3.5 Design of Arithmetic Circuits.
The notation 3.6 Multiplication. Before we discuss the general issue of multiplication, we should note that a binary number, b, can be multiplied by 2 simply by adding a 0 to the right of its least significant bit. This effectively moves all bits of b to the left, and we say that b is shifted left by 1 bit position. Thus, if b equals bn minus 1 bn minus 2, b1 b0, then 2 times b equals bn minus 1 bn minus 2, b1 b0 0. We have already used this fact in section 3.2.3. Similarly, a number is multiplied by 2k by shifting it left by k bit positions. This is true for both unsigned and signed numbers. We should also consider what happens if a binary number is shifted right by k bit positions. According to the positional number representation, this action divides the number by 2k. For unsigned numbers, the shifting amounts to adding k zeros to the left of the most significant bit. For example, if b is an unsigned number, then b divided by 2 equals 0 bn minus 1 bn minus 2, b2 b1. Note that bit b0 is lost when shifting to the right. For signed number sit is necessary to preserve the sign. This is done by shifting the bits to the right and filling from the left with the value of the sign bit. Hence, if b is a signed number, then b divided by 2 equals bn minus 1 bn minus 1 bn minus 2, b2 b1. For instance, if b equals 0 1 1 0 0 0 equals 24, 10, then b divided by 2 equals 0, 0, 1, 1, 0, 0 equals 12, 10, and b divided by 4 equals 0, 0, 0, 1, 1, 0 equals 6, 10. Similarly, if b equals 100, 1000 equals minus 24, 10, then b divided by 2 is equal to 110,000, 100 equals minus 12, 10, and b divided by 4 is equal to 111,000, and 10 equals minus 6, 10. The reader should also observe that the smaller the positive number, the more zeros there are to the left of the first one, while for a negative number there are more ones to the left of the first zero. Now we can turn our attention to the general task of multiplication. Two binary numbers can be multiplied using the same method as we use for decimal numbers. We will focus our discussion on multiplication of unsigned numbers. Figure 3.34 shows how multiplication is performed manually using 4-bit numbers. Each multiplier bit is examined from right to left. If a bit is equal to 1, an appropriately shifted version of the multiplicand is added to form a partial product. If the multiplier bit is equal to 0, then nothing is added. The sum of all shifted versions of the multiplicand is the desired product. Note that the product occupies 8 bits. 3.6.1 Array multiplier for unsigned numbers. Figure 3.34b indicates how multiplication may be performed by using multiple adders. In each step, a 4-bit adder is used to compute the new partial product. Note that as the computation progresses, the least significant bits are not affected by subsequent additions. 168 Number representation and arithmetic circuits CHAPTER3 multiplicand M 14 11101011 times multiplier Q 11 partial product 01110 multiplicand M 14 11101110 plus 1 times multiplier Q 11 011 partial product 111011110000 plus 11100000 partial product 2010101110 plus 1110100110 product P 154. A. Multiplication by hand.
1001110 product P 100
1001110 1001110 product P 154. A. Multiplication by hand. 1001110 product P 154. B. Using multiple adders partial product 0 M3Q0 times M3Q3 M2Q0 M2Q2 M1Q0 M1Q1 M0Q0 M0Q0 M3Q1 M2Q1 M1Q1 M0Q1 plus partial product 1 PP15 PP14 PP13 PP12 PP11 M3Q2 M2Q2 M1Q2 M0Q2 plus partial product 2 PP26 PP25 PP24 PP23 PP22 M3Q3 M2Q3 M1Q3 M0Q3 plus product PP7 P6 P5 P4 P3 P2 P1 P0. C. Hardware implementation. 168 Number representation in arithmetic circuits CHAPTER3 multiplicand M 14 11101011 times multiply.
168 Number representation and arithmetic circuits CHAPTER3 multiplicand M 14 11101011 times multiplier Q 11 partial product 01110 multiplicand M 14 11101110 plus 1 times multiplier Q 11 011 partial product 111011110000 plus 11100000 partial product 2010101110 plus 1110100110 product P 154. A. Multiplication by hand.
1001110 product P 154. B. Using multiple adders partial product 0 M3Q 0 M3Q 3 M2Q
100111010 product P 154. b. Using multiple adders, partial product 0 M3Q0 times M3Q3 M2Q0 M2Q2 M1Q0 M1Q1 M0Q0 M0Q0 M3Q1 M2Q1 M1Q1 M0Q1 plus partial product 1 PP15 PP14 PP13 PP12 PP11 M3Q2 M2Q2 M1Q2 M0Q2 plus partial product 2 PP26 PP25 PP24 PP23 PP22 M3Q3 M2Q3 M1Q3 M0Q3 plus product PP7 P6 P5 P4 P3 P2 P1 P0 C. Hardware implementation figure 3.34 multiplication of unsigned numbers.
M3Q2 M2Q2 M1Q2 M0Q2 plus partial product 2 PP26 PP25 PP24 PP23 PP22 M3Q 3 M2Q 3 M1Q 3 M0Q3 plus product PP7 P6 P5 P4 P3 P2 P1 P0 C. Hardware implementation figure 3.34 multiplication of unsigned numbers. Hence, they can be passed directly to the final product, as indicated by blue arrows. Of course, these bits are a part of the partial products as well. The same scheme can be used to design a multiplier circuit. We will stay with 4-bit numbers to keep the discussion simple. Let the multiplicand, multiplier, and product be denoted as M equals M3 M2 M1 M0, Q equals Q3 Q2 Q1 Q0, and P equals P7 P6 P5 P4 P3 P2 P1 P0, respectively. Figure 3.34c shows the required operations. Partial product 0 is obtained by using the AND of Q0 with each bit of M, which produces 0 if Q0 equals 0 and M if Q0 equals 1.
Tus PP 0 M3 ki 0 M2 ki 0 M1 ki 0 M.
Partial product 0 is obtained by using the AND of Q0 with each bit of M, which produces 0 if Q0 equals 0 and M if Q0 equals 1. Thus PP0 equals M3Q0 M2Q0 M1Q0 M0Q0. Partial product 1, PP1, is generated by adding PP0 to a shifted version of M that is AND with Q1. Similarly, partial product PP2 is generated using the AND of
Similarly, partial product PP2 is generated using the AND of Q2 with M shifted by another bit position and adding to PP1, and so on.
3 de junt multiplicatiu M3 M2 M1 M0 M1 fa M.
3.6 multiplication M3 M2 M1 M0 M1 fa M2 M0 fa M1 0 fa M0 0 square meters fa M3 M1 fa 0 cubic meters fa M2 fa M3 fa Q0 Q1 Q2 Q3 P7 P6 P5 P4 P3 P2 P1 P0 figure 3.35 a 4 times 4 multiplier circuit. A circuit that implements the preceding operations is arranged in an array, as shown in figure 3.35. In this figure the AND gates and full adders that produce the partial products are shown in blue, in the same way as the blue highlighted rows in figure 3.34c. The full adders are connected to form ripple carry adders. It is possible to design even faster multipliers by using other types of adders. 1. 3.6.2 Multiplication of signed numbers. Multiplication of unsigned numbers illustrates the main issues involved in the design of multiplier circuits. Multiplication of signed numbers is somewhat more complex. If the multiplier operand is positive, it is possible to use essentially the same scheme.
If the multiplier operand is positive, it is possible. 3.6.2 Multiplication of signed numbers. Multiplication of unsigned numbers illustrates the main issues involved in the design of multiplier circuits. Multiplication of signed numbers is somewhat more complex. If the multiplier operand is positive, it is possible to use essentially the same scheme as for unsigned numbers. For each bit of the multiplier operand that is equal to 1, a properly 170 number representation and arithmetic circuits, CHAPTER3 shifted version of the multiplicand must be added to the partial product. The multiplicand can be either positive or negative. 2m. Since shifted versions of the multiplicand are added to the partial products, it is important to ensure that the numbers involved are represented correctly. For example, if the two rightmost bits of the multiplier are both equal to 1, then the first addition must produce the partial product pp1 equals m plus, where m is the multiplicand.
If m mn1 m2 m1 m0, 10 pepes.
If m equals mn1 mn2 m1 m0, then pp1 equals mn1 mn2 m1 m0 plus mn1 mn2 m1 m00. The adder that performs this addition
comprises circuitry that adds two operands of equal length. Since shifting the multiplicand to the left to generate 2m results in one of the operands having n plus 1 bits, the required addition has to be performed using the second operand, m, represented also as an n plus 1 bit number. An n-bit sign number is represented as an n plus 1 bit number by using sign extension, that is, by replicating the sign bit as the new leftmost bit. Thus m equals mn minus 1, mn minus 2, m1 m0 is represented using n plus 1 bits as m equals mn minus 1, mn minus 1, mn minus 2, m1 m0. When a shifted version of the multiplicand is added to a partial product, overflow has to be avoided. Hence, the new partial product must be larger by 1 extra bit. Figure 3.36 illustrates the process of multiplying two positive numbers. The sign-extended bits are shown in blue. Part B of the figure involves a negative multiplicand. Note that the resulting product has two n bits in both cases. For a negative multiplier operand, it is possible to convert both the multiplier and the multiplicand into their 2's complements because this will not change the value of the result. Then the scheme for a positive multiplier can be used. We have presented a relatively simple scheme for multiplication of sign numbers. There exist other techniques that are more efficient, but also more complex. We will not pursue these techniques, but an interested reader may consult reference 1. We have discussed circuits that perform addition, subtraction, and multiplication. Another arithmetic operation that is needed in computer systems is division. Circuits that perform division are more complex. We will present an example in Chapter 7. Various techniques for performing division are usually discussed in books on the subject of computer organization and can be found in references 1, 2, 3.7 Other number representations. In the previous sections, we dealt with binary integers represented in the positional number representation. Other types of numbers are also used in digital systems. In this section, we will discuss briefly 3 other types: fixed point, floating point, and binary-coded decimal numbers. 3.7.1 Fixed point numbers. A fixed point number consists of integer and fraction parts. It can be written in the positional number representation as b equals bn minus 1 bn minus 2, b1 b0, b minus 1 b minus 2, b minus k.
3.7 Other number representations multiplicand m.
3.7 Other number representations multiplicand m plus 14, 0 1 1 1 0 multiplier q plus 11 times 0 1 0 1 1 partial product 0 0 0 0 1 1 1 0 0 0 1 1 1 0 plus partial product 1 0 0 1 0 1 0 1 0 0 0 0 0 0 plus partial product 2 0 0 0 1 0 1 0 plus 0 0 1 1 1 0 partial product 3 0 0 1 0 0 1 1 plus 0 0 0 0 0 0 product p plus 154 0 0 1 0 0 1 1 0 1 0 a positive multiplicand m 14 1 0 0 1 0 multiplier q plus 11 times 0 1 0 1 1 partial product 0 1 1 1 0 0 1 0 partial product 1 partial product 2 partial product 3 1 1 0 0 1 0 plus 1 1 0 1 0 1 1 0 0 0 0 0 0 plus
1110101 1 plus 110010 1101100 plus 0000000 product P 154 1101100 B negative multiplicand figure 3.36 multiplication of signed numbers. The value of the number is n-1 by v, b, equals I equals minus k times 2I. The position of the radix point is assumed to be fixed, hence the name fixed point number. If the radix point is not shown, then it is assumed to be to the right of the least significant digit, which means that the number is an integer. Logic circuits that deal with fixed point numbers are essentially the same as those used for integers. We will not discuss them separately. 172 Number representation and arithmetic circuits, CHAPTER 3.7.2 Floating point numbers. Fixed point numbers have a range that is limited by the significant digits used to represent the number. For example, if we use 8 digits and a sign to represent decimal integers, then the range of values that can be represented is 0 to plus or minus 999999999. If 8 digits are used to represent a fraction, then the representable range is 0.00000001 to plus or minus 0.999999999. In scientific applications, it is often necessary to deal with numbers that are very large or very small. Instead of using the fixed point representation, which would require many significant digits, it is better to use the floating point representation in which numbers are represented by a mantissa comprising the significant digits and an exponent of the radix r. The format is mantissa times r exponent. The numbers are often normalized, such that the radix point is placed to the right of the first non-zero digit, as in 5.234 by 1043 or 6.31 times 10⁻28. Binary floating point representation has been standardized by the Institute of Electrical and Electronic Engineers, IEEE. 3. Two sizes of formats are specified in the standard, a single precision 32-bit format and a double precision 64-bit format. Both formats are illustrated in Figure 3.37. Single precision floating point format. Figure 3.37 depicts the single precision format. The leftmost bit is the sign bit, 0 for positive and 1 for negative numbers. There is an 8-bit exponent field, E, and a 23-bit mantissa field, M. The exponent is with respect to the radix 2. Because it is necessary to sign 32 bits, ASME 8-bit 23 bits of mantissa plus 0 denotes excess, 127 exponent 1 denotes A, single precision 64 bits. 52 bits of mantissa 11-bit excess, 1023 sign, ASME exponent, B, double precision figure 3.37 IEEE standard floating point formats. 3.7 Other number representations. Be able to represent both very large and very small numbers, the exponent can be either positive or negative. Instead of simply using an 8-bit sign number as the exponent, which would allow exponent values in the range minus 128 to 127, the IEEE standard specifies the exponent in the XS 127 format. In this format, the value 127 is added to the value of the actual exponent, so that exponent equals E minus 127. In this way, E becomes a positive integer. This format is convenient for adding and subtracting floating point numbers because the first step in these operations involves comparing the exponents to determine whether the mantissas must be appropriately shifted to add/subtract the significant bits. The range of E is 0 to 255. The extreme values of E equals 0 and E equals 255 are taken to denote the exact 0 and infinity, respectively. Therefore, the normal range of the exponent is minus 126 to 127, which is represented by the values of E from 1 to 254. The mantissa is represented using 23 bits. The IEEE standard calls for a normalized mantissa, which means that the most significant bit is always equal to 1. Thus, it is not necessary to include this bit explicitly in the mantissa field. Therefore, IFM is the bit vector in the mantissa field. The actual value of the mantissa is 1.m, which gives a 24-bit mantissa. Consequently, the floating point format in Figure 3.37 represents the number 2e-127 value equals plus or minus 1 m times. The size of the mantissa field allows the representation of numbers that have the precision of about 7 decimal digits. The exponent field range of 2-126 to 2127 corresponds to about 10 plus or minus 38. Double precision floating point format. Figure 3.37b shows the double precision format, which uses 64 bits. Both the exponent and mantissa fields are larger. This format allows greater range and precision of numbers. The exponent field has 11 bits, and it specifies the exponent in the XS 1023 format, where exponent equals e-1023. The range of e is 0 to 2047, but again the values e equals 0 and e equals 2047 are used to indicate the exact 0 and infinity, respectively. Thus, the normal range of the exponent is minus 1022 to 1023, which is represented by the values of e from 1 to 2046. The mantissa field has 52 bits. Since the mantissa is assumed to be normalized, its actual value is again 1.m. Therefore, the value of a floating point number is 2e-1023 value equals plus or minus 1 m times. This format allows representation of numbers that have the precision of about 16 decimal digits and the range of approximately 10 plus or minus 308. Arithmetic operations using floating point operands are significantly more complex than signed integer operations. Because this is a rather specialized domain, we will not elaborate on the design of logic circuits that can perform such operations. For a more complete discussion of floating point operations, the reader may consult references 1, 2. 174 Number representation and arithmetic circuits, CHAPTER 3.7.3 Binary coded decimal representation. In digital systems, it is possible to represent decimal numbers simply by encoding each digit in binary form. This is called the binary coded decimal, BCD, representation. Because there are 10 digits to encode, it is necessary to use 4 bits per digit. Each digit is encoded by the binary pattern that represents its assigned value, as shown in Table 3.3. Note that only 10 of the 16 available patterns are used in BCD, which means that the remaining 6 patterns should not occur in logic circuits that operate on BCD operands. These patterns are usually treated as don't-care conditions in the design process. BCD representation was used in some early computers as well as in many handheld calculators. Its main virtue is that it provides a format that is convenient when numerical information is to be displayed on a simple digit-oriented display. Its drawbacks are complexity of circuits that perform arithmetic operations and the fact that 6 of the possible code patterns are wasted. Even though the importance of BCD representation has diminished, it is still encountered. To give the reader an indication of the complexity of the required circuits. We will consider BCD addition in some detail. BCD addition. The addition of 2 BCD digits is complicated by the fact that the sum may exceed 9, in which case a correction will have to be made. Let x equals x3 x2 x1 x0 and y equals y3 y1 y0 represent the 2 BCD digits, and let s equals s3 s2 s1 s0 be the desired sum digit, s equals x plus y. Obviously, if x plus y less than or equal to 9, then the addition is the same as the addition of 2 4-bit and signed binary numbers. But if x plus y greater than 9, then the result requires 2 BCD digits. Moreover, the 4-bit sum obtained from the 4-bit adder may be incorrect. There are 2 cases where some correction has to be made: when the sum is greater than 9 but no carryout is generated using 4 bits, and when the sum is greater than 15. So, Table 3.3 Binary coded decimal digits. Decimal digit BCD code 000010001140101070111070111810091001. 3.7 Other number representations plus x, y plus 0, 1, 1, 1, 0, 1, 0, 1 plus 7, 5, z 1, 1, 0, 0 plus 0, 1, 1, 0, 12 carry 1, 0, 0, 1, 0 s is equal to 2 times 1, 0, 0, 0, 8 plus y plus 1, 0, 0, 1 plus 9 z 1, 0, 0, 0, 1, 17 plus 0, 1, 1, 0, 1, 0, 1, 1, 1 carry s equals 7. Figure 3.38 Addition of BCD digits. That a carryout is generated using 4 bits. Figure 3.38 illustrates these cases. In the first case, the 4-bit addition yields z equals 7 plus 5 is equal to 12. To obtain a correct BCD result, we must generate s equals 2 and a carryout of 1. The necessary correction is apparent from the fact that the 4-bit addition is a modulo 16 scheme, whereas decimal addition is a modulo 10 scheme. Therefore, a correct decimal digit can be generated by adding 6 to the result of 4-bit addition whenever this result exceeds 9. Thus, we can arrange the computation as follows. Z equals x plus y if z less than or equal to 9, then s equals z and carryout equals 0 if z greater than 9, then s equals z plus 6 and carryout equals 1. The second example in figure 3.38 shows what happens when x plus y greater than 15. In this case, z equals 17, which is a 5-bit binary number. Note that the 4 least significant bits, z3 minus 0, represent the value 1, while z4 represents the value 16. To generate a correct BCD result, it is again necessary to add 6 to the intermediate sum z3 minus 0 to produce the value 7. The bit z4 is the carry to the next digit position. Figure 3.39 gives a block diagram of a 1-digit BCD adder that is based on this scheme. The block that detects whether z greater than 9 produces an output signal, adjust, which controls the multiplexer that provides the correction when needed. A second 4-bit adder generates the corrected sum bits. Since whenever the adjustment of 6 is made there is a carry to the next digit position, COOT is just equal to the adjust signal. The 1-digit BCD adder can be specified in Verilog code by describing its behavior as shown in figure 3.40. Inputs x and y and output s are defined as 4-bit numbers. The intermediate sum, z, is defined as a 5-bit number. The if-else statement is used to 176 number representation and arithmetic circuits CHAPTER3-4, bit adder detect if MUX4, bit adder sum 9 greater than 60XYCIN carry, out adjust 0Z30, Z4S COOT. Figure 3.39 block diagram for a 1-digit BCD adder. Reg module BCDAD, CIN, X, Y, S COOT. Input CIN, input 3 o'clock X, Y. Output reg 3 o'clock s, output reg COOT, for o'clock z, always at x, y, cin begin. Z equals x plus y plus cin, if z less than 10, COOT s equals z, else COOT s equals z plus 6, and N module figure 3.40 Verilog code for a 1-digit BCD adder. 3.7 Other number representations provide the adjustment explained above, hence it is not necessary to use an explicit adjust signal. If we wish to derive a circuit to implement the block diagram in figure 3.39 by hand, instead of by using Verilog, then the following approach can be used. To define the adjust function, we can observe that the intermediate sum will exceed 9 if the carryout from the 4-bit adder is equal to 1. Or if z3 equals 1 and either z2 or z1 or both are equal to 1. Hence the logic expression for this function is adjust equals carryout plus z3, z2 plus z1. Instead of implementing another complete 4-bit adder to perform the correction, We can use a simpler circuit because the addition of constant 6 does not require the full capability of a 4-bit adder. Note that the least significant bit of the sum, S0, is not affected at all, hence S0 equals Z0. A 2-bit adder may be used to develop bits S2 and S1. Bit S3 is the same as Z3 if the carryout from the 2-bit adder is 0, and it is equal to Z3 if this carryout is equal to 1. A complete circuit that implements this scheme is shown in Figure 3.41. Using the X3, X2, X1, X0, Y3, Y2, Y1, Y0 COOT4, bit adder 2, bit adder S3, S2, S1, S0, Z3, Z2, Z1, Z0, CIN Figure 3.41 circuit for a 1-digit BCD adder. 178 Number Representation and Arithmetic Circuits, CHAPTE, R3. 1-digit BCD adder as a basic block. It is possible to build larger BCD adders in the same way as a binary full adder is used to build larger ripple carry binary adders. Subtraction of BCD numbers can be handled with the radix complement approach. Just as we use 2's complement representation to deal with negative binary numbers, we can use 10's complement representation to deal with decimal numbers. We leave the development of such a scheme as an exercise for the reader. See Problem 3.19. 3.8 Examples of solved problems. This section presents some typical problems that the reader may encounter and shows how such problems can be solved. Example 3.6 Problem. Convert the decimal number 14959 into a hexadecimal number. Solution. An integer is converted into the hexadecimal representation by successive divisions B16, such that in each step the remainder is a hex digit. To see why this is true, consider a 4-digit number h equals h3, h2, h1, h0. Its value is v equals h3 times 163 plus h2 times 162 plus h1 times 16 plus h0. If we divide this by 16, we obtain VH0 plus equals H3 times 162 H2 times 16 plus H1 plus 16. Thus, the remainder gives H0. Figure 3.42 shows the steps needed to perform the conversion. 14959, 10 equals 3A6F, 16. Convert 14959, 10 14,959 divided by 16 is equal to 934 divided by 16 equals 58 divided by 16 is equal to 3 3 divided by 16 is equal to 0 934 58. Remainder 15 6 10 3 hex digit F6A 3 LSB MSB result is 3A6F 16 Figure 3.42 Conversion from decimal to hexadecimal. 3.8 Examples of solved problems. 179 Problem. Convert the decimal fraction 0.8254 into binary representation. Example 3.7. Solution. As indicated in section 3.7.1, a binary fraction is represented as the bit pattern b equals 0, b minus 1, b minus 2, b minus m, and its value is equals times plus times plus, plus times. VB minus 1 2 minus 1b minus 2 2 minus 2b minus m 2 minus m. Multiplying this expression by 2 gives b minus 1 plus b minus 2 times 2 minus 1 plus b minus m times 2 minus m minus 1. Here, the leftmost term is the first bit to the right of the radix point. The remaining terms constitute another binary fraction, which can be manipulated in the same way. Therefore, to convert a decimal fraction into a binary fraction, we multiply the decimal number by 2 and set the computed bit to 0 if the product is less than 1 and set it to 1 if the product is greater than or equal to 1. We repeat this calculation until a sufficient number of bits are obtained to meet the desired accuracy. Note that it may not be possible to represent a decimal fraction with a binary fraction that has exactly the same value. Figure 3.43 shows the required computation that yields 0.8254, 10 equals 0.11010011. 2. Convert 0.8254 times 2 is equal to 0.6508 times 2 is equal to 0.3016 times 2 is equal to 0.6032 times 2 is equal to 0.2064 times 2 is equal to 0.4128 times 2 is equal to 0.8256 times 2 is equal to 0.6512 times 2 equals 0.8254. 10 equals 1.6508, 1.3016, 0.6032, 1.2064, 0.4128, 0.8256, 1.65121, MSB 10100, 1.30241, LSB 1 figure 3.43 conversion of fractions from decimal to binary. 180 number representation and arithmetic circuits CHAPTER 3. Example 3.8 problem. Convert the decimal fixed point number 214.45 into a binary fixed point number. Solution. For the integer part, perform successive division by 2 as illustrated in figure 1.6. For the fractional part, perform successive multiplication by 2 as described in example 3.7. The complete computation is presented in figure 3.44, producing 214.45, 10 equals 11,010,110.0111001. 2. Example 3.9 problem. In computer computations, it is often necessary to compare numbers. To forbit sign numbers, x equals x3, x2, x1, x0, and y equals y3, y2, y1, y0, can be compared by using the subtractor circuit in figure 3.45, which performs the operation x minus y. The three outputs denote the following. A z equals 1 if the result is 0, otherwise z equals 0, n equals 1 if the result is negative, otherwise n equals 0, a v equals 1 if arithmetic overflow occurs, otherwise v equals 0 equals. X show how z, n, and v can be used to determine the cases x, y, and x greater than or equal to y, less than or equal to y, y greater than y. Solution. Consider first the case x less than y, where the following possibilities may arise. If x and y have the same sign, there will be no overflow, hence v equals 0. Then for both positive and negative x and y, the difference will be negative, n equals 1. If x is negative and y is positive, the difference will be negative, n equals 1. If there is no overflow, v equals 0. But the result will be positive, n equals 0. If there is overflow, v equals 1. Circle plus equals. Therefore, if x less than y, then nv1. X equals y is detected by z equals. The case if z1. Then, x less than or equal to y is detected by z plus, and circle plus v equals 1. The last two cases are just simple inverses, x greater than y plus, and circle plus v equals 1, and x greater than or equal to y if and circle plus v equals 1. Example 3.10 problem. Write Verilog code to specify the circuit in figure 3.45. Solution. We can specify the circuit using the approach given in figure 3.23, as indicated in figure 3.46. Note that the statement assign z equals s will produce 1 only if s equals s3, s2, s1, s0 equals 0, 0, 0, 0. Thus, it represents the 4-bit NOR function z equals s3 plus s2 plus s1 plus s0. Instantiating each full adder separately becomes awkward when large circuits would be the case if the comparator had 32-bit operands. An alternative is to use the generic specification presented in figure 3.24 as shown in figure 3.47. 3.8 examples of solved problems. Convert 214 is equal to 0 plus 2 to 107 20 LSB 107 is equal to 1 plus 2 to 53 to 153 is equal to 1 plus 2 to 26 to 126 is equal to 0 plus 2 to 13 to 013 is equal to 1 plus 2 to 6 to 160 plus 2. 3, 2 is equal to 0, 3, 1 plus 2. 1, 2 is equal to 1, 1, 1 plus 2. 0, 2 is equal to 1 MSB 0.900 0.45 times 2 is equal to 1.800 MSB 10.90 times 2 is equal to 1.60 0.80 times 2 is equal to 1.20 0.60 times 2 is equal to 0.40 0.20 times 2 is equal to 0.80 0.40 times 2 is equal to 1.60 0.80 times 2 is equal to 1 LSB 214.45 10 equals. Figure 3.44 conversion of fixed point numbers from decimal to binary. 182 number representation and arithmetic circuits CHAPTER3 Y3 Y2 Y1 Y0 FA X3 FA X1 S1 FA C1 X0 S0 C0 FA C3 X2 S21 S3 C2 C4 VNZ. Overflow, negative, 0. Figure 3.45a comparator circuit. Wire module comparator, X, Y, V, and Z. Input, 3 o'clock X, Y. Output V and Z. 3 o'clock S. 4:1 C. Full add stage 0, 1 foot B1, X0, Y0, S0, C1. Full add stage 1 C1, X1, Y1. S1 C2, full add stage 2 C2, X2, Y2, S2 C3, full add stage 3 C3, X3, Y3, S3 C4. Assign V equals C4 C3, assign N equals S3, assign Z equals S, N module full add CIN, X, Y, S coot, input CIN, X, Y, output S coot. Assign S equals XY CIN. Assign coot equals X and Y. X and CIN. Y and CIN. N module figure 3.46 structural Verilog code for the comparator circuit. Always X and Problem. Figure 3.35 depicts a 4-bit multiplier circuit. Each row in this circuit consists example 3.11 of 4 full adder, FA, blocks connected in a ripple carry configuration. The delay caused by the carry signals rippling through the rows has a significant impact on the time needed to generate the output product. In an attempt to speed up the circuit, we may use the arrangement in figure 3.48. Here, the carries in a given row are saved and included in the next row at the correct bit position. Then, in the first row, the full adders can be used to add 3 properly shifted bits of the multiplicand as selected by the multiplier bits. For example, in bit position 2, the 3 inputs are M2Q0, M1Q1, and M0Q2. In the last row, it is still necessary to use the ripple carry adder. A circuit that consists of an array of full adders connected in this manner is called a carry-save adder array. What is the total delay of the circuit in figure 3.48 compared to that of the circuit in figure 3.35? Solution. In the circuit in figure 3.35, the longest path is through the rightmost tuple adders in the top row, followed by the 2 rightmost FAs in the second row, and then through all 4 FAs in the bottom row. Hence, this delay is 8 times the delay through a full adder block. In addition, there is the AND gate delay needed to form the inputs to the first FA in the top row. These combined delays are the critical delay, which determines the speed of the multiplier circuit.
184 Number representation en Arithmetic Circuits CHPTER3 0
184 Number representation in arithmetic circuits CHAPTER30M3Q0M2Q0M1Q0M0Q0 Fa 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 M3Q1 M2Q1 M1 Q1 M0 Q1 M2 Q3 M1 Q3 M0 Q3 0 0 0 M2 Q2 M1 Q2 M0 Q2 M3 Q2 M3 Q3 P7 P6 P5 P4 P3 P2 P1 P0 Figure 3.48 Multiplier carry save array. In the circuit in Figure 3.48, the longest
path is through the rightmost FAs in the first and second rows, followed by all 4 FAs in the bottom row. Therefore, the critical delay is 6 times the delay through a full adder block plus the AND gate delay needed to form the inputs to the first FA in the top row. Problems. Answers to problems marked by an asterisk are given at the back of the book. Asterisk 3.1 Determine the decimal values of the following unsigned numbers. A 011101110, 2 B 101 110 0111, 2 C 3751 8. D. A 25F 16E. F0 16 asterisk 3.2 Determine the decimal values of the following ones complement numbers. A 011 101 1110. B 101 110 0111. C 111 111 1110 asterisk 3.3. Determine the decimal values of the following 2's complement numbers. A 011 101 1110. B 101 110 0111. C 111 111 1110. Problems 185 asterisk 3.4 Convert the decimal numbers 73, 1906, minus 95 and minus 1630 into signed 12-bit numbers in the following representations. A. Sign and magnitude. B. 1's complement. C. 2's complement. 3.5 Perform the following operations involving 8-bit 2's complement numbers and indicate whether arithmetic overflow occurs. Check your answers by converting to decimal sign magnitude representation. 001101110, 0111, 01011101111 plus 010000101 plus 1101110 plus 1011100, 001101110, 0111 01011101001 minus 001010111 minus 110101110 minus 1110110. 3.6 Prove that the XOR operation is associative, which means that 11 circle plus E circle plus C equals 11 circle plus C circle plus C. 3.7 Show that the circuit in Figure 3.4 implements the full adder specified in Figure 3.3a. 3.8 Prove the validity of the simple rule for finding the 2's complement of a number, which was presented in Section 3.3. Recall that the rule states that scanning a number from right to left, all zeros and the first one are copied, then all remaining bits are complemented. 3.9 Prove the validity of the expression overflow equals Cn circle plus Cn minus 1 for addition of n-bit signed numbers. 3.10 Verify that a carryout signal, CK, from bit position k minus 1 of an adder circuit can be generated as CK equals XK circle plus YK circle plus SK, where XK and YK are inputs, and SK is the sum bit. Asterisk 3.11 Consider the circuit in Figure P 3.1. Can this circuit be used as one stage in a ripple carry adder? Discuss the pros and cons. The operation of transistors shown in the figure is described in Appendix B. Asterisk 3.12 Determine the number of gates needed to implement an n-bit carry look-ahead adder, a Semigno fan-in constraints. Use and, OR, and XOR gates with any number of inputs. Asterisk 3.13 Determine the number of gates needed to implement an 8-bit carry-look-ahead adder assuming that the maximum fan-in for the gates is 4. 3.14 In Figure 3.17 we presented the structure of a hierarchical carry-look-ahead adder. Show the complete circuit for a 4-bit version of this adder, built using two 2-bit blocks. 3.15 What is the critical delay path in the multiplier in Figure 3.35? What is the delay along this path in terms of the number of gates? 3.16 Write a Verilog module to describe the 4x4 multiplier shown in Figure 3.35. Synthesize a circuit from the code and verify its functional correctness. Asterisk 3.17 Consider the Verilog code in Figure P 3.2. Given the relationship between the signals in and out, what is the functionality of the circuit described by the code? Comment on whether or not this code represents a good style to use for the functionality that it represents. 3.18 Design a circuit that generates the 9's complement of a BCD digit. Note that the 9's complement of D is 9 minus D. 186 Number representation and arithmetic circuits CHAPTER3 CIGIPSCESIVDDCI plus 1 Figure P3.1 Circuit for Problem 3.11. Module Problem 3_17 IN Out. Input 3 o'clock IN. Output Reg 3 o'clock out. Always at IN. If IN equals 4 foot B0101. Out equals 4 B0001. Else if IN equals 4 B0110. Out equals 4 B0010. Else if IN equals 4 B0111. Out equals 4 B0011. Else if IN equals 4 B1001. Out equals 4 B0010. Else if IN equals 4 foot B1010. Out equals 4 B0100. Else if IN equals 4 B1011. Out equals 4 B0110. Else if IN equals 4 B1101. Out equals 4 B0011. Else if IN equals 4 B1110. Out equals 4 B0110. Else if IN equals 4 B1111. Out equals 4 B1001. Else out equals 4 foot B0000. And module Figure P 3.2 The code for Problem 3.17. Problems 187 3.19 Derive a scheme for performing subtraction using BCD operands. Show a block diagram for the subtractor circuit. Hint: subtraction can be performed easily if the operands are in the tens complement, radix complement representation. In this representation, the sign digit is 0 for a positive number and 9 for a negative number. 3.20. Write complete Verilog code for the circuit that you derived in Problem 3.19. Asterisk 3.21 Suppose that we want to determine how many of the bits in a 3-bit and sign number are equal to 1. Design the simplest circuit that can accomplish this task. 3.22 Repeat Problem 3.21 for a 6-bit and sign number. 3.23 Repeat Problem 3.21 for an 8-bit and sign number. 3.24. Show a graphical interpretation of 3-digit decimal numbers, similar to Figure 3.11. The leftmost digit is 0 for positive numbers and 9 for negative numbers. Verify the validity of your answer by trying a few examples of addition and subtraction. 3.25 In a ternary number system, there are 3 digits, 0, 1, and 2. Figure P 3.3 defines a ternary half adder. Design a circuit that implements this half adder using binary encoded signals, such that 2 bits are used for each ternary digit. Let A equals A1 A0, B equals B1 B0, and sum equals S1 S0. Note that carry is just a binary signal. Use the following encoding: 0 0 equals 0 3, 0 1 equals 1 3, and 10 equals 2 3. Minimize the cost of the circuit. AB carry some
00000110220211022102211 figure P 3.3 ternary half adder. 3.26 Design a ternary full adder circuit using the approach described in problem 3.25. 188 Number representation and arithmetic circuits, CHAPTER3. 3.27 Consider the subtractions 26 minus 27 is equal to 99 and 18 minus 34 is equal to 84. Using the concepts presented in section 3.3.4, explain how these answers, 99 and 84, can be interpreted as the correct signed results of these subtractions. References: 1C, Hamaker, Z, Vranesic, S, Zaki and N, Manjikian, Computer Organization and Embedded Systems, 6th edition, McGraw-Hill, New York, 2011. 2D, A, Patterson and J, L, Hennessy, Computer Organization and Design the Hardware/Software Interface, 3rd edition, Morgan Kaufman, San Francisco, California, 2004. 3. Institute of Electrical and Electronic Engineers, IEEE. A proposed standard for floating point arithmetic, Computer 14, number 3, March 1981. Pages 51 to 62.